So the vast majority of attacks that occur on information systems occur through vulnerabilities in software. We have developed a mentality about security that identifies a very strong perimeter security infrastructure, firewalls and intrusion detection systems, because what's on the outside is substantially scarier to us. The unknown is scarier to us than the threats and vulnerabilities that are on the inside. So we turn our defenses towards the outside, the unknown, that tends to be a little more frightening to us. Yet, in all reality, over 80% of all attacks and all violations of security occur from within, from on the inside. And the vast majority of these attacks are attacks on vulnerabilities that exist inside software. So how does this happen? This happens because software vendors typically want the product to work, and they want to get it to the market as quickly as possible. Make it work and get it done fast. They've never ever been concerned about the security, and I shouldn't say never ever, but they rarely are concerned about the security of the application itself. And the developers have never been trained for implementing security in their code. It's never been a requirement, never been an objective. The objectives, again, make it work and get it done fast. So these things have been their only priorities, and it hasn't been stressed to them that this should be a component of their design. We also have gotten used to the bugs in the software. It's become a routine thing for us. We understand that there's patching routines that are ongoing and continuous, and it's just part of the system. And so we have developed a certain tolerance for these vulnerabilities in the software. And this also is kind of a bad thing. We also don't hold the software vendors liable for the vulnerabilities in their software, the bad code that they write. So again, we aren't holding the right people responsible. So more and more we have to apply pressure on the software vendors to make their code more secure. It's estimated that about 1% of all code is a vulnerability. And with Windows 2000 having about 50 million lines of code in it on average, you're looking at about 500,000 vulnerabilities that eventually will either get exploited or will get recognized and fixed, or we never even find them. With Windows XP and Vista, we're looking at 60 million lines of code to 75 million lines of code. We're looking at 750,000 vulnerabilities designed into the operating system. So they are there at a very high rate. The way the vulnerabilities present themselves is buggy software is released to the market. They made it work and they got it out the door fast and they're generating revenue, and for a software developer, that's the golden rule. That's the way it works. Hackers then find vulnerabilities in this buggy software, and they then perform their exploits, take the pieces they want to take with their exploits, but then very often what they do is they publish these vulnerabilities and exploits on the hacker websites. So now it becomes publicly known that there are vulnerabilities in this particular application or in this particular operating system. When the vendors learn of this, now that they've been published as having vulnerabilities, they now typically are forced to react. And they would react by developing a patch or a fix for this particular vulnerability and then releasing that patch. Now, very often, though, the vendors just drag their feet on this. Why? Because nobody holds them accountable. Nobody pressures them to producing those patches. So, eventually, for the majority of them, they will develop a patch. And then they release the patch to the marketplace, and we, of course, at the user side of it, are always must be diligent on implementing these patches on a regular basis. You'll also notice a loop back from the vendor developing a patch back to hackers find new vulnerabilities. That's because the patch is nothing more than another piece of software, and 1% of all software has a bug in it. So the patch has a vulnerability that needs a patch, and so it's an ongoing cycle. So the concept needs to be security must permeate the entire software development lifecycle. Each and every stage of that software development lifecycle or system lifecycle must be permeated with security in mind. We have to continually analyze, even at the idea stage, is this going to violate my security policy for the organization, or is this going to introduce vulnerabilities into other security components? So security must permeate the entire process. Now we're going to look at some software development tools. We're going to look at object-oriented programming, and then some security issues related to programming. One of the premier software development tools is called computer-aided software engineering, or CASE tools. Now a CASE tool is a very sophisticated platform that a software developer performs his design and development work within. So a software developer goes to school for several years and learns his software engineering skills, but then he has to go to school for another 6 months to a year to learn these very sophisticated CASE tools. Now when he does this, if he does this, the CASE tool actually is a huge aid to the proper development of software because it has pre-programmed structures and procedures that help the software developer produce his software more quickly, more efficiently, and it also has double checks to validate that the security and other mechanisms that might get installed in the software are cleaned up before the software is ever actually released. These other mechanisms I'm describing would be something called a maintenance hook, which is a sort of a backdoor for the programmer. As a programmer is testing a certain piece of his code, he doesn't want to have to log in and work through a menu to get to a certain location in the program. So what he does is he builds in something called a maintenance hook. And this maintenance hook lets him jump right to this one spot in the program so he can test it, refine it, test it, refine it, etc. Well, now these maintenance hooks, if they don't pull these maintenance hooks back out, these are vulnerabilities. Bad guys find these back doors and can violate the access control mechanisms that are built into the program. So a CASE tool keeps track of things like these maintenance hooks and will actually, at the end, assuming the software developer is following the rules, at the end will programmatically and systematically march through the entire program and extract these maintenance hooks because they should not be left in. These are vulnerabilities, the type of vulnerabilities I've been describing. This is a screen capture from one of the computer-aided software engineering tools. So our software has become more and more complex over time. We have things like virtual machines and multiple desktops and other sophisticated components like middleware that actually make our software processes more and more complex all the time. What does this mean? Well, the greater the complexity, the more opportunity for vulnerability, and it means that our security mechanisms must be more and more sophisticated all the time. So again, what this translates to is we really must permeate the entire development process with security. Because we have this very complex scenario, we have to be testing each and every one of these constructions. We can't just say, well, when I built it something like this the last time, it was pretty secure, so it was all good. Because as we start linking these modules together in ways that we had never linked them together before, we introduce new opportunity for vulnerabilities. Many times these components that I'm describing are pre-programmed objects or components that are stored in a library. The term, the dynamically linked library, very bottom bullet here, deals with these are libraries that are built into the operating system, and they store components, software procedures that can be referred to over and over again. Well, the difficulty here is we have this huge collection or library of these procedures, and they can be strung together in an infinite number of combinations. Each one of these combinations must be tested individually for security consideration. So here we're going to look at the history, if you will, of programming languages. We're going to start with the first generation language. That's the 1GL, first generation language, is machine language. Now, machine language is not human readable, but it is the language that is understood by the CPU. In an earlier domain, we looked at applications that spawn processes and processes that spawn threads, and those threads are the instructions that the CPU can execute directly. Well, that thread is written in machine language. So machine language actually provides a couple of different things. First, it secures the intellectual property of the program because it's not human readable. But that's the downside of it, is that it can't be modified when we need to make a change or when we're in development stages. So again, 1GL is called machine language. It's not human readable, and in a way it's a form of encrypting or securing your intellectual property, your program. The second generation language is called assembly language. Now, assembly language is very rudimentary, very basic, and it used 8 bits per byte, but it also had to be translated into machine language. Now, assembly language to the skilled, to the trained, was somewhat human readable. So it was written by humans. The code would be written by humans in this hexadecimal representation, and then would be translated into machine language. And the software that translated the assembly language code into machine language was called an assembler. So this assembler program actually interpreted the assembly language into machine language. Where we are right now is at high-level languages. We are in the 3GL, third generation languages. Now this is where we have BASIC and Fortran and COBOL and C++ and C++ and all the others. And we actually are moving closer to fourth generation language. So we're somewhere about 3.5 GL is what most people say. We write our programs in higher level scripting languages where a specialized syntax in a command actually implements more than one instruction at a time. It could be approximately a whole procedure that is tucked into this one script. So again, we're working on high-level languages. Now again, these are written in scripts. So again, this is a human-readable form. Again, it can't be processed by the CPU directly. It has to be translated or interpreted into machine language. So I will either run the script through an interpreter while I'm in development stages, so that every time I run my script it gets interpreted on the fly and gets fed to the CPU. Or I can compile the script once I'm done with it and I'm satisfied I want to lock it down so nobody can make any changes to it, and also nobody can read any of the code. So I will compile it, and now it is permanently translated into machine language. Again, it's not human readable. It is now the executable that we see on our computers. 4GL is fourth generation language. This is considered very high level language, very abstract, and we aren't quite there yet, but this is where we're dealing with large components of software that get strung together more along the lines of higher level object-oriented programming. We're not quite there yet, so that still has to be defined what 4GL truly is, other than it's higher than where we are now. And then fifth generation language is the actual natural language, where a human would say, computer, I need you to balance my checkbook. And the computer would actually automatically generate its own code, understand what you said, generate its own code to actually perform the work that you've requested. This approaches artificial intelligence. So again, this is where ultimately we hope to be going. We're approximately at about 3.5 right now. And as I indicated, our scripts from assembly all the way up need to be interpreted during development. That's so I can keep my script in readable form, and I can modify it and then test run it through the interpreter where it is translating or interpreting my script into machine language on the fly every time I run it. That means it's a slower process because I have to translate it before I can execute it. But it also means that my script is readable so that I can modify it. I modify, interpret, and execute, test it. I modify again to refine, interpret, and run it so that I can test it, etc. So the interpreter is used principally during the development phases. However, once I get my code developed, I want to lock it down, and I also want to hide the intellectual property that is the source code. So that's when I will permanently compile my script into machine language. Machine language, again, is not readable. It's almost a form of encryption, if you want to think of it that way. So it hides my intellectual property, and also now nobody can modify my code. It also now will execute substantially more rapidly because it's already translated. I don't have to translate it again. These are the executables that you find on your computer system. So in the old days, we wrote scripts, and every statement, every process that we wanted to implement, we would have to code it out with a specialized syntax for each and every step that I wanted to accomplish. Today, more and more, we deal with object-oriented designs or component-oriented designs where I have pre-programmed modules. One module might be for authentication purposes. One module might be for summation purposes or taking an average calculation of a column of numbers, something along these lines. And I have these pre-programmed components in a library, and I just use a script to string these huge chunks of program together. So the newer approach is more the object-oriented design versus the statement-by-statement procedural design that we used to do in the old days. Some benefits of the object-oriented programming are that they're modular. We have these pre-programmed chunks of code that already do this one step, but it's something that we need to do very often. So I can simply reuse this component over and over and over again. And the cool thing about it is, as I implement that, instantiate that object another time, I can modify its behavior a little bit. So it's kind of like the same as it was over here, only now it's a little bit different. So I have modularity. The deferred commitment means I can modify it on the fly because it is a complete and cohesive component, and it has an input and it has an output, and what happens inside, it doesn't really affect the rest of the system. So I can modify subtly the way it behaves without modifying the entire system. Again, they're reusable, and because these are components are designed or produced because it's something we all need to do fairly often, it lends itself very naturally to satisfying the business needs that the program is trying to satisfy. So these components, when they're sitting on the shelf in the library, these are referred to as classes. Now a class is this chunk of code that has not been put into a program yet. So a class is kind of like a recipe that I can instantiate in the program. When I instantiate the class into a program, it now becomes an object. So it's only an object once I've tucked it into a program. When it's still sitting on the shelf, it's called a class. Now the class, as I said, is a component or an object, and it has many characteristics or attributes. I can modify those attributes before or as I instantiate the object. In other words, I can take one class that says draw me a shape, and as I instantiate it, I can define the shape as a square. Or the next time I instantiate it, I can define that the shape is going to be a circle. And the next time I instantiate it, I can define that the shape will be a triangle. So I can modify these attributes and implement the class or instantiate the class into different objects. This is referred to as polymorphism. We're going to see this in just a few moments. Here, again, is the object. So first we had the class. That's the recipe on the shelf. Now that we've instantiated it into a program, it's referred to as an object. And we have all the attributes defined now. So now it actually is a functioning component inside a program, and it actually is performing some process work, and it has input and it has output. And the process that we're implementing inside is referred to as a method. We're going to see that in a moment as well. Here we go. The processes that are performed within the object are referred to as the object's method. That's the work that the object is performing on the data. And then we have an input to the object and we have outputs from the object. Those communications between objects are referred to as messages. You need to understand what a method is and what the message is. Messages are communications between objects. The method is the processing that occurs within the object. What is this object doing? Some examples are we might be requesting user credentials. We might be adding numbers to one account while we're subtracting numbers from another account as we transfer money. Or we might be making a simple query of a database. So what we see in the diagram here is that we have strung together a collection of objects, and we have a start message going into this program now, and that message as it enters the first object, that first object is going to perform its method on the data that is the message. And that information now gets output to another object, and this collection of objects are going to process the data through and produce some resulting output, some message out to the environment. Now these objects are complete components and they are isolated from one another. This provides a form of encapsulation or black boxing or abstraction or layering or data hiding, all these things. That's what an object does for me. This is an opportunity to implement security in our software development. So again, the process that's occurring and the manipulations that are occurring to the data inside the object are and can be hidden from all other objects in the program. Again, this is the opportunity for encapsulation, data hiding, layering, abstraction, all these things. And here's the example of that this modularity provides this black box approach. Object 1 sends a message to Object 2. Object 1 has no idea what Object 2 is going to do to that data, nor does he care. Object 2 does his work internally, outputs a message to Object 3, and Object 3 has no idea what Object 2 did to that data or message. So again, this is an opportunity to implement security through the code. Earlier I described these attributes that exist within a class, and as I instantiate that class and create an object, I firm up or nail down these attributes, and I have the opportunity to modify these attributes as I instantiate different copies of that same class, different instantiations of that same class. This is referred to as polymorphism. Poly means many, morph means change. So I can take the same class and make many changes to that class as I instantiate that class into different objects, and I can have these different objects now performing different types of work. As we see in the diagram, we have an object that was instantiated. It probably used to say x plus y equals z, and now we instantiate it a second time and we say x plus y equals z, only we've modified some of the attributes. In the first instantiation we say 3 plus y equals z. In the second instantiation we say 1 plus y equals z. So we've modified an attribute, and I have now instantiated from the same class, instantiated two different objects. This is referred to as polymorphism. Here's another example where the class is to draw an object, or draw a shape, for example. So as we instantiate the class that says draw a shape, we define to draw the shape of a triangle, a circle, or a square. So again, this is an example of polymorphism. Now this is another characteristic of object-oriented programming. That's called polyinstantiation. Polyinstantiation says multiple instances. Poly, multiple, instantiation, instances. So what this says is I can take the same class and instantiate it multiple times, and I can modify them so that they are different. So polyinstantiation basically modifies one instance of the same object as a different object, multiple instances. Now where we use this primarily, polyinstantiation, comes with an attempt to defend against what's called aggregation and inference attacks. In the example we see here on the slide, if we had a battleship named the Oklahoma and it was on a covert mission to deliver weapons to the Ukraine, being covert, only our top secret level people are allowed to know this. However, everybody else in the environment knows that we have this ship named the Oklahoma, and if it's not docked at the berth, then where is that ship? So we have to have some second instance of the truth to tell the rest of the people about where the ship is. Otherwise, they will identify, well, the ship is missing, and we've been having some trouble in Ukraine. I wonder if it's on a covert mission to the Ukraine, delivering some weapons or something like this. And you see how we can take these different unrelated details and aggregate them together and infer some conclusion that takes us to a level of knowledge higher than we're authorized to know. So what we do to defend against this is we now polyinstantiate a second story of a second instance of this story about where the ship Oklahoma is. So what we do is the people below top secret, we tell them the Oklahoma is actually delivering food to African nations. So they recognize that the ship is missing, oh, it's delivering food, and they stop wondering about it, and as a result they don't have the impetus to aggregate and infer knowledge that they aren't authorized to know. Another aspect of object-oriented programming, as we're looking at the objects themselves, is an element called cohesiveness. Now, fundamentally, cohesion is a force that holds an object together. There's a cohesive pressure on the surface of a water droplet that holds the water molecules together and makes it form the droplet and not disperse into vapor. So that's the definition of cohesion. In object-oriented programming, what this identifies is that we have a module that is self-sufficient, it is not ambiguous, it carries out a single task. That's a high level of cohesiveness. One input does its work, its method, one output, that's it. That's a highly cohesive object. This is generally considered to be a good thing in object-oriented programming. As we define these objects, we want them to have a high level of cohesion. If objects have a low level of cohesion, what this means is they need perhaps more inputs and they are performing more processes and they have more outputs. So it's a little less predictable and it's a little more dependent on other services, other inputs. So this generally makes it a little more difficult to implement properly, and it especially makes it more difficult to secure because of all the variables that might be affecting the security of this particular programmatic component. It's generally considered that if you have a low cohesion object, you should break this one object into multiple smaller objects that have a higher level of cohesion, single task. And here's the example of that. On the right we see an object with low cohesion. It has multiple inputs and multiple outputs. On the left what we see is an object of high cohesion. And what we've done is we've taken that low cohesion object and broken it up into two discrete objects, both of which now have a high level of cohesion. Now the next concept here deals with coupling. Coupling is pretty much the dependency that an object has on other objects. In other words, how many inputs are required for this particular method to perform, to execute properly. The more inputs that are required, the more difficult it is to properly implement this object, and the more difficult it is to secure the object. So we want a low level of coupling. One input is ideal. The more inputs you have, the higher the coupling or dependency requirements, and therefore the less secure the object is. So we want high cohesion and low coupling. That's the ideal nature of a good object. In this section we're going to be looking at distributed computing. This is where I have multiple computers operating on the same information to develop some grand output. We're going to have several computers, different processes perhaps running different data sets and different procedures, but I'm going to aggregate information from these different pieces, perhaps do some additional processing, and then produce some grand result. We're going to look at COM, Component Object Model, and DCOM, which is Distributed Component Object Model. These are creations from Microsoft. The next one we'll look at is ORB and CORBA. ORB is Object Request Broker, and CORBA is the platform that the ORB lives in. So CORBA is the common ORB architecture. And then we're going to look at Java with Java 2 Enterprise Edition and their implementation of how to implement distributed computing in the Java environment. Then we're going to look at some mobile code like ActiveX and Java Applets. These are the pieces of program that are typically downloaded from server to client and then are executed on client side. So mobile code runs on client side. That's a significant thing to recognize. So let's dive into this and see where it takes us. Distributed computing deals with multiple computers working together on the same common project, if you will, to produce some grand output. And again, we're going to look at the Common Object Request Broker Architecture, CORBA, that utilizes ORBs. The ORB lives on a single box. CORBA is the architecture that allows those ORBs to communicate and share information. Those are platform-independent components. They can live on any piece of hardware, any operating system, as long as that device is CORBA compliant. Whereas COM and DCOM are strictly Microsoft components, and they only run on Microsoft boxes. It's a Microsoft creation invention and only runs on Microsoft. And finally, we'll look at Sun's Java Beans, Java components, Java Beans, and even the Java Sandbox. First, we'll look at ORB. ORB is Object Request Broker. Again, it is a procedure or a collection of programs that work together, typically on a single box, and it's doing its own collection of processing. Now, an ORB is considered, by the way, all of these are considered middleware. They live between the server, which is the data repository, and the client, which is the end user that needs the information. So it isn't actually either one of those. It's actually in between. So it's all referred to as middleware. COM, DCOM, ORB, and CORBA. This is all middleware stuff. And again, so we have an ORB that lives on a single box, and the CORBA architecture says another ORB can request information from this ORB, so they can share information back and forth. That's the major concept behind ORB. CORBA is the architecture that allows the ORBs to communicate. So each of the boxes that are running ORB components must be compliant with the CORBA architecture specification. And again, this is platform independent. This is one of the things that make it very high utility, is it doesn't matter what operating system or what type of CPU the box is running. If it is CORBA compliant, you can run ORBs and you can actually communicate with other CORBA compliant systems. Again, Microsoft does not use ORBs or CORBA natively. Microsoft uses COM and DCOM, which we're going to talk about in just a moment. So COM is Component Object Model. Again, a Microsoft creation. And COM was originally designed to be used only on a single box. So COM was a way that one program could share information with another program, such as the ability to take a table out of an Excel spreadsheet and embed it into a Word document. So now I have a table inside the Word document. This is called object linking and embedding, OLE. We're going to bump into that in a few minutes. And this was all a byproduct of COM. So COM is the grandfather, if you will, of object linking and embedding, dynamic data exchange, and net dynamic data exchange, as well as the grandfather of DCOM. We're going to be talking about the majority of those here in a few minutes. So again, COM lives only on a single box. It does not allow communications between other COM objects in other computers. DCOM is two boxes that run COM that now can communicate over the wire. So distributed COM is COM on a long wire, if you want to think of it that way. Now I can have a process on this computer, an Excel spreadsheet, for example, and a Word document on this computer, and I can extract a table out of the Excel spreadsheet from over here and drop it into a Word document over here. That's what DCOM gives us. It is the networking architecture for COM objects, just like CORBA is the networking architecture for ORB objects. So Microsoft's DCOM is comparable to CORBA. And finally, a third player in the arena is the Java platform. And the Java version 2 Enterprise Edition is a platform independent system that allows programs or applications to be developed in the Java language, and then these can be executed and utilized by any computer, no matter what their hardware or operating system is. There is a server-side and a client-side model. The server side is referred to, the applet is called the Java Bean. That's the server side of the applet, and then of course there's a Java application on the client side that connects up to the Java Bean on the server that is actually doing the work. So thin client and the Java Bean is the server-side component. So here's an example that shows us how the J2EE platform works. On the right-hand side, what we see is your data store. This is simply a database, not necessarily any processing happening here. This is principally just storage and data input and data output. Then in the second column over, the server-side business logic, this is where we actually perform the processing. So this is the engine that's accessing the data in the databases, is actually performing manipulations and perhaps tallies and summaries and things along these lines. So it's actually massaging the data set. On the next one over, server-side presentation, this is actually the portal that the clients on the far left will be connecting to. So the clients connect to the portal or the presentation servers. That would be like a web server or some application server that they can connect to. This is strictly a portal, and it is isolated from the processing engines. Very often we do this for isolation and for security purposes. If the clients, who might be anonymous clients, can connect to the server, they could be attacking that server and might steal confidential data. So all we give them is the portal. The clients now connect only to the portal. The real data and processing lives back on the server side. So again, this is designed for security and for performance and functionality. So 4 stages. We have storage, we have processing, we have portal services, and then we have the client-side applications. Now, back to COM. COM, as I said, was the grandfather of object linking and embedding, DCOM, Dynamic Data Exchange, and Network Dynamic Data Exchange, NetDDE. And object linking embedding was the example that I described to you a little while ago, where I could take a table out of an Excel spreadsheet and embed it into a Word document. I could even make the link, the connection, dynamic. And we're going to look at a slide here in just a minute that shows us that. So here, what we see is if I simply embed an object, I take the object, which is a blue object, the blue box in the upper left-hand corner, and I embed that into a document. Some other, like that's, the blue is the Excel spreadsheet, the black is the Word document. And I can take that table and just drop it into the Word document. And if I just embed the table into the Word document, there it sits, and I can even modify the data inside the table in the Word document. But what you notice is I've modified it by adding the little orange square. You notice the original remains untouched. It's not been modified. So if I just embed the table, it's like making a second copy of it and tucking it into this Word document. If I actually link the table to the Word document, now that I've embedded and now linked the table inside the Word document, if I modify the table by adding the orange square, this is over on the right-hand side now, you see how that modification commutes back to the original. So these are now permanently and dynamically linked. If I modify in one area, it updates the other area. Just as if I modified the original Excel spreadsheet, it would actually update inside the Word document. So if I'm linking them, that's a dynamic connection. The 2 tables remain synchronized. If I simply embed the object, they are 2 separate copies now, and there is no dynamic link associated. Mobile content is content that is generally added to a server application. It is downloaded from server to client, and it runs on the client side. And the whole purpose of this mobile content is to improve the feature richness of the client's experience as he's connected to that server in a session. So mobile code is, again, generally a good thing for the clients. We want the cartoons, and we want the bells and the whistles and the dynamic nature of our session on the server. But at the same time, this is an excellent way for a bad guy to distribute his malware. So mobile code and active content is quite dangerous. It has to be carefully scrutinized and controlled. Otherwise, this is how a great deal of malware gets distributed. Some examples of active content in mobile code are the Java applets, ActiveX controls, macros, and even email attachments that are executables. So these are forms of mobile code and active content. Again, they get downloaded to the client side and run client side. Some of the malware that can be introduced by this mobile code is at the very bottom bullet, the Trojans, the backdoors, viruses, worms, and other forms of malicious code. ActiveX is a Microsoft creation. Again, this is an extension of the COM grandfather, as we had described earlier. ActiveX is Microsoft's implementation of their mobile code, and again, while it provides feature-rich content, it is very often a vehicle for the distribution of malware. So Microsoft has introduced a technology called Authenticode to try and secure ActiveX controls. This screen shows us the Authenticode query for a particular ActiveX control. You can configure your browser to either allow all ActiveX controls, to prompt you, which is a warning if the control is not signed, or to block it if it's not signed. Now, the way Authenticode works is you would write an ActiveX control, you would ship that ActiveX control to Microsoft along with a check, and they will actually test it to make sure there's no malware, and then digitally sign your ActiveX control. Now you can install that on your web server, and all the client's browsers that are configured to either warn or block if it's not signed, these will now automatically accept your Microsoft approved, authenticated ActiveX control. Now the downside of Authenticode is it does not quarantine the ActiveX control. In other words, it doesn't isolate that piece of software. That software is still there on your system. It's just the operating system is disallowing, and I say operating system, the browser application is disallowing its execution. By the way, ActiveX can only be run natively in Internet Explorer. I hear there's an add-on for Firefox to allow ActiveX controls, but this type of content is really optimized for the Internet Explorer browser. So Java, invented by Sun Microsystems. It is a platform-independent programming architecture. The applications or applets are all written in JavaScript, and they are all written in exactly the same language. The great thing about this is they don't need to be ported to other platforms. Other forms of program, if I write a program on a Microsoft and Intel CPU, and I want to run it on a Sun microsystem running Unix, I have to port it to that hardware and software platform. And that's a very expensive process, and it often doesn't translate correctly. So the porting process is always complicated. The way Java solves this problem is all applets are written in exactly the same language. It never has to be ported. What Java provides is called the Java Sandbox, or the Java Virtual Machine. So they have a different Java virtual machine for each hardware and operating system platform, and the Java applet runs inside this Java virtual machine. So the inside of the Java virtual machine is identical 100% of the time. All Java applets will run in any of the virtual machines, and as long as you install the right virtual machine on your hardware platform, it interfaces correctly with your platform and operating system. So the outside of the Java virtual machine communicates with your platform, and this allows the Java applet to be platform independent. Now Java uses a programming code called bytecode, and this is something you'll need to know for the exam. Bytecode means you're running a Java script or Java applet. So the Java Sandbox is a virtual machine, as I described. There is a different Java Sandbox or virtual machine for each hardware and operating system combination, and as long as you install the proper Java Sandbox on your computer, then you can run 100% of all the Java applets that have ever been written. Now this was a form of abstraction, isolation. It was a security boundary. What happened inside the Java Sandbox could only stay inside the Java Sandbox, so we were told, until somebody broke out of the Java Sandbox and infected a host machine with malware. So the sandbox, while it is an abstraction layer, it's a security boundary, it's not as absolute as we once thought it was. It's still a Java applet that has malware inside can still break out of the sandbox, the virtual machine, and infect the host computer that's running the Java virtual machine. As I said before, Java is written in what's called bytecode, and the way Java secures its Java applets is by running a bytecode verifier to try and validate the legitimacy of the code. So the bytecode verifier is Java's approach to securing their Java applets, just like Authenticode was Microsoft's implementation to validate the correctness of ActiveX controls. In this section, we're going to be looking at databases and the components that operate within databases, different types of databases. We're going to look at database management systems. We're going to look at some database models, give you a whole bunch of definitions related to databases. You'll need to know these. Look at some security issues relative to databases and their applications. We're going to look at the development of knowledge and information out of the databases. This is referred to as data mining that produces metadata. And then we're going to extend that a little further and take a look at knowledge systems. So a database is a collection of information that is stored in a meaningful way, and there's an application that can access this database and that can modify the information that's being stored there as well. Now that application and the procedures that allow the modification of the information is generally managed by a database management system. This is the system around the database store itself. The database management system allows for things such as the creation of users to assign privilege or permission. It has the procedures that allow for the storage, the removal, the querying, the modification of the data that's stored inside the database. These are all facilitated by the database management system. And again, that lives around the engine called the database itself. That's the data store. So the data store is just the storage place. The database is just the storage space, and the database management system is all the other ancillary services that keep that database engine functioning. We have a handful of different types of databases that we'll be looking at. We're first going to look at the hierarchical database. This is referred to as a flat database. It is a tree structure. We'll look at the network database, object-oriented, relational database, and then object relational database. So here's a quick overview of 4 different types of these databases. In the first example, upper left-hand corner, we see the hierarchical model. Now this is again, called a flat database. It is a tree structure, very much like folders on a hard drive. And what you should recognize about this is each child has a single parent. That's one of the characteristics of a hierarchical database model, is that each child has a single parent. And as we move to the right, we see the network model. The difference between the hierarchical model and the network model is that what you'll recognize is a child can have more than one parent. And so this is a different feature. It allows extra flexibility in the design of the hierarchical database. But it also adds to it some complexity. That complexity brings along with it additional potential vulnerability. So the hierarchical single parent, the network model, multiple parents for each child, potentially. Could be one, could be multiple. In the lower left-hand corner, we see the relational model. In the relational model, this is a 3-dimensional database where we use primary keys and foreign keys to build relational links between different tables. So the information is stored in tables, and there are links between these tables that build relations between this piece of information and that piece of information. And then finally, in the object-oriented model in the lower right, this is a database that stores not only data, but also stores programmatic objects, as we described earlier in object-oriented programming. So this is a database that holds the program and the data, and can be dynamically modifying data all inside the database itself. This is the newest, one of the newer types of databases, and it's very powerful, very dynamic. So here's kind of a timeline of how databases have grown. Originally, we just had flat files like a Word document or an Excel spreadsheet. And in the 70s, we introduced the hierarchical and the network. Again, the major difference is single parent or multiple parents. And then we grew to the relational database, and in the 90s and beyond, we're now getting more into the object-oriented type of databases, much more sophisticated and much more powerful. So the hierarchical database is a flat database, again, a tree structure, very simple to build, very easy to assemble, but fairly limited in the versatility, because each child can only have a single parent. In a network database, again, it adds the capability of having multiple parents for each child. And this, again, affords us a little more flexibility and a little more versatility. It's more of forming a lattice structure, as indicated in the slide. Now, in the object-oriented database, this is a database that stores not just data objects, but it also stores objects such as programmatic objects. It also can store very non-textual types of data, such as videos, image files, and audio clips. So here now we have the data set, and we have the processes that modify or manipulate that data set. And together, this makes for a very powerful type of database. And here's an example of this object-oriented database. Stored within the database are the object-oriented programming objects with all the strengths and features and flexibility of object-oriented programming, and they are stored all within the database along with the data elements themselves. So we add all that to the database management system, and we have a very versatile, very functional, very powerful database. So some of the benefits of object-oriented database models. again, because it has the programming built into it, or a lot of programming that can be built into it and stored within the database, I don't need such a sophisticated program on the outside that queries and then modifies data sets and then stores the information back in. It all happens internally rather than an external application that will modify the data that lives internal to the database. And again, here we see the client is interacting with these database objects rather than through a database application. He deals directly with the object. Why? The object is the application. It's the process. Remember, there's a method inside that object that is actually manipulating potentially the information, the data that is stored in the database as well. So we have a more direct relationship to the process and the data without having some front-end application that is going to actually go in and extract data, modify it, and then have to put it back. It all happens within the database. Now, a relational database is another of the newer forms of databases. This is referred to as a three-dimensional database because data is stored in tables, and those tables can be linked to other tables. We can actually define relationships from an element in this table to a record in that table. And as a result, this allows a very versatile, very functional structure for the data set, and it allows for easier data storage and manipulation. Here's a small sample of a table in a relational database. There's some definitions you must know on this particular slide. First, what we see is the table. We see a row in the table is referred to as a tuple, T-U-P-L-E. Now this term comes to us out of a mathematical phrase that deals with a single, a double, a triple, a quadruple, a quintuple, a sextuple, and ... we get the term n, tuple, n being a variable, and they just throw the n away, and that refers to a tuple is a series of related elements, and that's what a row is. So in the row that's now called a tuple, we see that these are all elements that are related to this primary key of G345 in the first row. Now again, the row in the table is referred to as a tuple. Another term for this is a record. So we have a record, a tuple, or a row. They're all the same thing. And again, what does that mean? It's a series of related elements. Element, by the way, is the name or the definition of that data that lives inside the cell. The cell is the intersection of a row and a column. That's called the cell. That's the empty container. The data that lives within that is referred to as the element. What else do we have here? We have the vertical column. The vertical column first is defined by a field. That's the top label. That's defining a field. Now that field, like in the attribute column described here in the diagram, the field that's highlighted there is called color. The field name is color. That is an attribute for the tuple. So the tuple has these attributes: product ID, size, color, and design. Those are the attributes, and they define a field. And the column is referred to as an attribute. So these are some terms you need to know. So let's run through them quickly again. First, we have the table itself. Then we have a row that's also called a record or a tuple. We have a column that is called a field or an attribute. We have the field name, which is the top level. And then we have the primary key, which is something now adding new information here. Primary key is a special field on each table, and it must exist, and it must uniquely identify that row in the table. In other words, the primary key must exist for each record, and it must be unique for each record in the table. So those are two checks, validation checks that we have for primary keys. We're going to see that in a few minutes. Let's move forward. So here we're going to look at a couple other components here. We see the row here. They're calling this a record. Again, we know it as a tuple or a row or a record. We see the field. We call that an attribute or a field, yeah. And then we have the data value. We called that also an element. And the empty space, if the word Chicago wasn't written in one of those fields, that empty space is called the cell. So there's those definitions again. So again, the primary key, this is a special value that exists on each and every table in a relational database. It identifies uniquely that record or that tuple in the table. These primary keys are used as the indexing component. So this is where this is the source of the point of reference for each record in a table. Now here what we see is the way that we link these tables together, which makes them the relational database. I relate the primary key from one table in a different table as the foreign key. So you see how we've used the primary key of P478. That's a primary key in the top table. That becomes a foreign key in the lower table. So this is the link or the relation between these two tables. So now that one cell, P478, in the lower table implies all the data that the row implies in the top table for P478. And this is how the relational component of relational databases come together. Now the foreign key has a couple additional validation checks. If I implement a foreign key in a table, that foreign key value must exist as a primary key in a foreign table. And here they are. So let's go back to now the primary key. The primary key, and by the way, these are rules that the developer of a database, a relational database, should be validating. These are components of the primary key that should be double checked before the record is ever allowed to be entered. This validation check is referred to as the entity integrity validation for a primary key. Two checks. The first check says if you're going to build a row in a table, it must have a primary key. You can't have an empty primary key and have a row that exists. Second thing is that primary key for that record must be unique in that table. In other words, I can't reuse that same value in multiple records. So those are two entity integrity validation checks for primary keys. Now when I use that primary key in a foreign table, it becomes a foreign key in that second table. And for foreign keys, we have another validation that we need to check, and that's referred to as referential integrity. If I generate a foreign key down here, which links it to a primary key in another table, that value must exist as a primary key in the other table. It cannot be linked to a null field. So that is referred to as the referential integrity validation check for foreign keys. Now let's take a quick look at the difference between the way relational databases are generally structured versus the way object-oriented databases are structured. Relational databases, we would have a table for employees. And somewhere on that employee table there would be a field that is a foreign key that identifies what department that employee works in. And that would link to a department table. So that table then has a primary key that also may have another foreign key that identifies a job within that department. So that links to a job table. So that's the way a relational model is assembled. Whereas in object-oriented database models, what we do is for each component in the database, we build a class for that particular object, such as an employee class, a manager class, a secretary class. And remember, those classes are a collection of pre-programmed steps that include attributes or details about employees or managers or secretaries, and it also includes programming code that allows us to modify that information based on some procedure. So the object modeling, we build classes, whereas with relational modeling, we build tables. So now that we have a little bit of understanding about how the database works in the background, let's take a look at how the client actually connects to the database. What is that connector that runs between client and the actual data set itself? This list that we see on the slide here shows us Open Database Connectivity, the ODBC. We're going to look at Object Linking and Embedding Database. We're going to look at ActiveX Data Objects. We're going to look at Java Database Connectivity. And then we're going to look at the Extensible Markup Language. So what we see in this diagram is at the bottom of the diagram we see the actual data stores themselves down at the bottom. That's where all the data is held. Those are all your database servers. but those database servers all need to work together. So each different type of database server needs a particular translator, if you will, so that it can be accessed by a common application. That application speaks one language. We need to be able to translate that application's language into those different types of database servers down below. So that's what this bottom tier component is, the Oracle driver, the Sybase data driver, the DB2 driver. Those are all translators. And that's pretty much what we're talking about here. Now, then we move up to the middleware section. That's where these drivers all come together to a common point. That's where we have a common language finally, and now using that common language we can filter down through those drivers and access any data set down at the lower level. And then at the higher end, at the very top row, this is where the user application lives, and the user application then communicates in that same language as the middleware language. So that's the structure that we see here in this diagram. That's how clients actually connect to the actual data sets on the back end. We're going to be talking about that, that second row up, those different drivers that translate between the native database language and some other common language that can be used by all other databases themselves and all applications. So the first of these drivers that we're talking about, we're going to look at, is called ODBC, or Open Database Connectivity Driver. This is a piece of software that lives between the database itself, and it speaks the native database language on the low end, but it then translates that database information into a different format that is compatible with some external application, or maybe it's just some common language that all the databases get translated to, so this common application can access all the data sets. So basically all this guy does is he translates the information from one format into a more compatible format for other purposes, and that's really all he does. He's just a translator from one application's format and language to some other database language and format. Now, one of the newer guys on the block is referred to as the OLE database, or Object Linking and Embedding Database. Now, OLE is a grandchild of COM, as you recall, and OLE allowed us to take like an Excel spreadsheet table and embed that into a Word document. Then I could either embed it or I could dynamically link it, and that's a lovely thing. This takes it way beyond that. This says that this driver will allow the application to access not just databases, as the database says here in the slide, but it also allows the application to access even documents like Word and Excel and PowerPoint and other COM-based applications. So this is a very powerful new driver, and this is actually being hailed as the replacement for ODBC. ODBC has been around forever. This is the new kid on the block, and he's going to take over ODBC. The kicker here, though, is because this is based on COM, this says this is only usable on a Microsoft system. So while he's got the latest and greatest of all power and all horsepower, he's only usable on Microsoft platforms. He actually is based on an extension of ActiveX, and as we see in the slide, it refers to the ActiveX data objects. So he can actually access these ActiveX components. He can access Excel spreadsheets. He can access databases, and so he's a very powerful dude, but only lives on a Microsoft box. And again, here we see where this guy lives. We have different databases at the bottom in the diagram. In one case, we translate from SQL through an ODBC driver up to the OLE database, and then from there we extend up closer to the client side at the top of the diagram. So again, this guy, as I said, is the replacement for ODBC, and he is he's the new kid on the block. He's going to replace ODBC, strictly though on a Microsoft operating system. ActiveX data objects, again, this is an extension of COM, and is client-side processing. This guy runs on the client side, but allows the client to access OLEDB components and other COM components. So again, this is one of those pieces in this structure that allows clients very liberal access to data sets of virtually any platform. Now, a competing platform is Java, of course, running on Sun Microsystems, and they have their own implementation. Just like Microsoft has their OLEDDB, they have their Java database connectivity, and they call that the JDBC driver. So this is the same thing as ODBC, only it's for Java databases, Java applications, and does the same kind of translation from a Java database into a more common database for an application. As you see at the very bottom bullet, they even have a driver to go from Java to ODBC, and now ODBC that connects to any other type of application or database. And we've seen a diagram very similar to this already. On the back-end system to the right, that's where our databases live. That's the data set themselves. Then we have the business logic. That's the processing engine. Again, those two sets of servers would always be secured on the LAN side, never publicly exposed. So that is a boundary. We have the data store and the data processes all live on a very secure environment. That's why we have these isolation layers. But then we have the presentation layer. That's what would be our web server or our application server that connects up to the client side, where we have the client side of the application, either the thin client application or a browser or something along these lines that connects up to the presentation server. The presentation server then goes and makes queries of the business logic servers that are actually doing the processing, and those business logic servers are actually extracting data, manipulating data from the data stores on the back end. And yet another format that we have for manipulating data and accessing data is called the Extensible Markup Language, or XML. This we see primarily in web servers and accessing of databases, producing dynamic content and rendering that content as an XML file that your browser can present. So again, this is a way to, using a web browser, simply build a web application running on XML that can dynamically go query, massage, extract, manipulate data, and then dynamically present that to you as a rendered XML document. And here's a diagram showing us that, how the client browser connects up to the XML system. The application is the blue box in the middle that has the components that are doing the querying, the data massaging, the manipulation, and then automatic rendering of the results and producing the XML output. So now we're going to dive into another arena, primarily talking about transaction processing and ensuring that the integrity of the data remains high. We're also going to look at a certain type of attack on information, and then we're going to look at ways to try and protect the information from being revealed. This would protect confidentiality by implementing something called database views. So the first thing we're going to look at is referred to as concurrency control. This is where concurrency says that a record will remain with a high level of integrity. And an example of this would be a distributed database where I have two copies of the same database. This is often done for geographic distribution and for fault tolerance, since I have two copies, etc. But if a user can connect to this copy of the database and another user can connect to this copy of the database, it's possible that they could both modify the same exact record at the same time, store their changes, and then when replication occurs between these two data sets, they realize that we have a version conflict. And so we now have to resolve that. This is concurrency control. So disallowing this version conflict situation is what concurrency control is all about. The example I gave you is when we had a distributed database. This can even happen on a single database if we don't implement proper locking of records. And we're going to be taking a look at that. So again, the whole point of this is so that two people don't open up the same record at the same time and attempt to modify the data differently, causing a version conflict. These are databases are very busy. There might be 10 people or 100 people or even thousands of people accessing the same data sets all simultaneously, and it's very possible and very likely that every now and again two people want to modify the same record at the same time. And so the database has to protect against that happening. This would cause a violation of the integrity of information and could cause a loss of data. If one record overwrites your changes, somebody else's changes, you actually can lose data. This is a violation of availability of information. So one way that we are able to maintain a higher level of integrity in a database is by means of something called the transaction and the ability for a transaction to either complete or roll back. So a transaction is declared in a programmatic structure. I declare begin transaction, and then I have different steps, programmatic steps that I'm performing inside the transaction, and finally I have an end transaction statement. And what happens is, if I start a process where I pass through a begin transaction statement, if I don't reach the end transaction declaration in a timely fashion, the system will automatically roll out any steps from the begin transaction point that it has taken, and as if the transaction never was started. So this is referred to as rollback. So again, once I start a transaction, if I don't complete the transaction in a timely fashion, all steps that I have taken within that transaction get rolled back out of the database as if the transaction was never begun. Another mechanism we have inside this transaction processing is referred to as checkpoint control. This is where the database automatically backs up the state of the transaction during the transaction. Now, this is generally implemented when we have a very long transaction processing time. So I might periodically, every 10 minutes, for example, just do a background save. That's called a checkpoint. That's where the system automatically saves the state of the system in very often a temporary register, temporary buffer somewhere, just in case we never complete or the system crashes or something happens before we can complete. We know exactly what we've done, so we could actually roll those steps back out because we never got to the end transaction statement. And here's a diagram showing us this. We have this process A that may take a long period of time. And this is happening inside inside the dynamic RAM that is volatile memory. In other words, these steps that we've taken are happening here in volatile RAM. However, periodically I do a checkpoint. I just take a snapshot of what's going on over there, and I record it in an area that if the power goes away and the system goes down, this is non-volatile, so it will remain intact. And that way, when the system comes back up, I can roll back those changes out of non-volatile RAM into the database and restore the database to the point just prior to that process beginning or that transaction beginning. That's called a checkpoint. Now, there's another aspect here that I want to mention. It's called a save point. While the checkpoint is automatically system generated, a save point is human generated. Very often in our systems, we have the ability to go hit the save button every now and again. That would be called a save point. So checkpoints are automatic and they're system generated. Save points are human generated. It's kind of like I'm about to do something dangerous here. I just want to make sure I have a record of where I am before I implement this dangerous procedure. Another mechanism we have is called locking controls. Now, a locking control is generally on the same data set. If user A accesses a record and starts to modify it, he gets read and write permissions to that record. And if user B needs to access that same record, he gets read-only access. In other words, it's locked for user B. That way, he can't make concurrent modifications as user A. So user A now has read-write privilege, user B has read-only privilege. As soon as user A releases that record, user B's privilege escalates now to a point where he has read-write, but he's now looking at the data set that user A just had modified. So this is a locking mechanism to ensure that we don't run into concurrency problems. And here's an example of that locking mechanism. Here, what we have is two different transactions. What we have is a customer on the phone, and we have two different database workers that are searching for a seat reservation for whoever it is that's on the telephone. So the worker on transaction A gets a phone call. We're looking for the best seat for this customer. He opens up the database and he identifies that seat number 18 is available. Well, a split second later, a second operator gets a call and somebody's asking for a seat at that same presentation, whatever it may be, and he opens up the same database. Well, seat number 18 is still available, so that record hasn't been locked. There's the problem. In a more secure environment, when transaction B was started, it would show that transaction A has already accessed seat number 18, and therefore the next seat would be number 19. Does that make sense? And then from there, because in this example there are no locks, both transactions are able to proceed and allocate seat number 18 in conflict to two different customers. So this example shows us what happens when we do not have these locks in place to protect against concurrency problems. This is also referred to as version conflict problems. We have two records now for seat 18 that show two different people registered to that same seat. Another mechanism is referred to as the two-phase commit. This again helps us with our transaction processing and helps to protect the integrity and, in some cases, the availability of our information. So in this case what we have are a two-step transaction where step 1 occurs and we've got that completed, and then step 2 occurs and we get that completed, and only after we complete step 2 can I start to make commitments on the transactions, the steps within the transaction that occurred. So again, if I don't get to the second step in a timely fashion, I would roll back and not commit the first step either, and not commit either of the steps. So this is referred to as the two-phase commit. Now, as a developer is building an application, a database application specifically, these are 4 validation checks that the developer should be looking at. 4 aspects of his design that he should be providing to help us afford protection of confidentiality, integrity, and availability. The first step on databases we're looking for is something called atomicity. And that says basically, if you have a transaction, we need to get through all steps in a timely fashion. If we don't reach that end transaction statement, we never commit and we roll back all changes. So we get through all steps or we don't complete any steps. It's all or nothing. That's atomicity. And again, that implies the rollback feature if I don't get to that end transaction statement. The next one down on the acid test is called consistency. That says that the transaction must meet internal and external consistency checks. That says that my math says if I have 100 widgets plus 100 widgets, the math better equal 200 widgets. That's internal consistency. External consistency says if Bobo sells 10 widgets, he better input that he sold 10 widgets, and he better not input that he sold 5 widgets and pocketed the difference. This would be an external consistency check. And again, these 2 validation checks are to prove or ensure the integrity of the information. So internal consistency, the programming and the math and the processing doesn't violate integrity. External consistency says whatever happened in reality, that information gets input into the database in reality. That we have ways to validate that Bobo really sold 5 widgets or 10 widgets, whatever the number actually was. That's consistency. The next one is called isolation. Isolation says when I start a transaction and I might be performing these interim steps and I haven't reached the commit stage yet, don't show the user any of these steps. Don't show them the results of these steps. Only show them after the commit has taken place. That's the only time they're allowed to see the entire process or transaction. So we are isolating the user from these interim steps because they aren't real until we hit the commit button. So we isolate him from this information. And then finally, the last one is D for durability. Durability says once I hit that commit button and the transaction commits to the database, that transaction is durable. It's persistent. It cannot be deleted. If it was a mistake, you have to generate a whole new transaction to reverse it. And now we have the error transaction and the corrective transaction on the books, and we don't have to worry about somebody deleting transactions out of the book and actually perhaps trying to steal money or commit some form of fraud. So we want to perform the acid test on our database, and our database application should be designed with these concerns in mind: atomicity, consistency, isolation, and durability. Now, we've talked about this already, aggregation and inference attacks. Aggregation is pulling together details that you're authorized to see and then putting them together and inferring some information that you are not authorized to see or know. So in our database, we should build in protective measures to defend against aggregation and inference attack. One of these defensive mechanisms is polyinstantiation. Remember, we talked about this. This is where top secret guys, I tell them the truth, but anybody below top secret, I have to make up a story because I can't just say, well, I can't tell you what's happening. What does this do? This spurs curiosity, and now aggregation and inference is what's probably going to happen next. So I have to satisfy their curiosity by telling them essentially a lie about this particular event or piece of information. So again, aggregation is combining details that you are authorized to know that are not necessarily related, but when you put them together and you analyze them, you can infer information that you are not authorized to know. Another mechanism we have to protect against confidentiality and et cetera types of violations of our database is something called the database view. And a database view might say that while I have 5 tables and I have 10 rows on each table, you're allowed to see 3 of the tables and only 2 of the rows on each of those tables. So I will subtract or hide information from you based on your level of privilege. In the diagram we see the subject has 3 types of privilege. He has the red privilege, the green privilege, and the blue privilege. And only where those 3 intersect, that is the small amount of information in the database view that we're going to present to that end user. So again, it's a way to isolate the user from data or hide data from the end user. So this is called a database view. This is also called a constrained view or a restricted view. And this slide pretty much pulls it all together to show the various components that should go into the development of a database application. We have the database engine itself. We have the ODBC drivers that translate from that unique database engine into a more common language. We have all sorts of concurrency checks, validity checks, integrity validation checks, translation processes, and then we have the front-end application with a portal that will actually allow the clients to connect in and not touch the actual application server or database servers themselves. So again, this is the big picture of database applications. Next, we're going to take a look at data warehousing, which is a large collection of databases. We're going to look at data mart, which is a subset of that data warehouse. So it's a smaller collection of databases. And then we're going to look at metadata. Metadata is data about data, but it isn't the data itself. We'll be looking at that in a little more detail. So a data warehouse. Basically, it's a large collection of databases from perhaps and probably many different sources on many different types of data. It isn't necessarily all in the same vertical market or anything along these lines. It's just a huge collection of databases, and we're maintaining them on these cluster servers, on a SAN perhaps. We've got backups and fault tolerance and redundancy and et cetera, et cetera. This is a data warehouse. Data warehouse, again, the databases are from different sources. Now the data is normalized. This is a one-year class all by itself about data normalization. Fundamentally, what we're trying to do is we're trying to clean up the data. Ideally, if I can only have one instance of any piece of data, such as your home address, I don't want that on 15 different tables. I want that address on one table, and then I will link where it's needed the 14 other places. I just have a pointer pointing back to that one original location. That way, if there's a modification that's required, I make it one time and all the other 14 locations know about it. Rather than if I have 15 copies of that data, I have to modify it 15 places, and it's never complete and it's never very efficient. So the fundamental component of data normalization is remove all the redundancies of those data elements. Don't have your address in there 15 places. Have it in there once with 14 pointers back to that one location. The next one is that it is there to be mined. In other words, the data mining has to do with massaging the data and extracting useful information out of it. Now, this useful information, this summary, is metadata. So the results of data mining is metadata. And metadata might be that I have 15 types of tequila in my database, rather than what the 15 types are. The 15 types, exactly what they are, that is the actual data itself. Metadata is summary data about the data. And then we take that summary information and we clean it up to prepare it for the user. Sometimes they didn't pay us for that much information, so only give them the 3 pieces out of the 10 that they're actually paying us for. Sometimes it's about confidentiality. while the report shows 15 details, at your level of authorization, I can only show you 3 of them. And that's called data sanitization. And then finally, after I've sanitized the information, I now export that information into some friendly format for the intended user. So here is pretty much that information represented graphically. We have the data input down below. That's from many different sources, many different locations, and that all must be put together in some common language. That's the ODBC driver, and then we bring it into the data warehouse. Now that DTS is a data transformation system or server, and it's actually going to be the importing side of the ODBC driver. So I take the raw source, I convert it into a common language for the transformation server, and then I dump that information, now that it's been transformed into the proper format, into the data warehouse. Now from the data warehouse, I can run querying or analyzing applications that massage or perform the data mining for me, and that produces the metadata that I'll now sanitize and format properly for end user reporting. Now there's one other little component there called the data cube. A data cube is a small subset of related information, typically smaller than a data mart. Data marts very often have unrelated data, much more information than I really need. But a data cube is a little more refined, it's a smaller set, it's a little more cohesive in its nature and its structure. Again, metadata is data about the data. It isn't the data itself that lives in the database, but it's summary data about that data. The data dictionary is a component that is part of the database management system, and it contains something called the schema. Now the schema is the structure of the database. It's the fact that I have 3 tables, and each table has 10 fields, and this field is the primary key here, and this primary key is used as a foreign key here. And what I'm going to do is I'm going to take all these numbers and I'm going to add them together, and then I'm going to multiply by that number over there. That information is called the schema. The schema is the structure of the database. It is not the data in the database, it's the structure of the database and the relationships and the processes that all are carried on for that particular collection of data in the database. So that's the data dictionary. It contains the schema. Now the data dictionary also contains metadata. It knows that on that first table I have 53 tuples or 53 rows or 53 records. It also knows that if I added let's say this is an inventory table, and I have 10 of these and 5 of these and 9 of those, it'll add all those up and tell me how many items I have in inventory. That would be another piece of metadata. It isn't the actual data itself, but it's summary data about the data. So the data dictionary contains the schema, and it contains metadata, and it lives within the database management system as part of this database. Now a data mart is a smaller subset of the data warehouse. I take this data warehouse that has many, many databases, hundreds, perhaps thousands of databases from different sources. For my analysis purposes, some project I'm working on, I might need a database on, and the classic example is male shoppers and diapers and beer. That's the example. So I'm going to take out a database on male shoppers and diapers in how often they're purchased, and beer, how often that's purchased. And what I might pull together from this small data mart as I mine the data and extract metadata is I might determine that anytime a male shopper buys diapers in the store, 94% of the time that male shopper that just bought diapers is also going to buy beer. So this is the metadata that I extract from this data mart. Out of 4,000 databases, I pulled together 3, I mined it to produce metadata, and my conclusion is 94% of the time when a male shopper buys diapers, he also buys beer. Now, what do I do with this information? I turn it into knowledge. What this says is, from now on, anytime I put diapers on sale, I'm not going to put beer on sale, and vice versa. If I put beer on sale, don't have diapers on sale, so that I'm making my profit somewhere. Also, what I might conclude out of this is maybe what I need to do is I need to have a beer display next to the diapers or close enough to the diapers so that the guy who comes in who is going to buy diapers says, oh yeah, I think I'll pick up a six-pack too. And so this then begins the transformation of information into knowledge, how to do something really insightful with the information. And here is that the example where I have multiple databases on the back end, and I transform them into a data warehouse. Then from that large, giant data warehouse, I'll pull out different subsets called data marts. I'll perform my data mining on those data marts and produce cohesive data sets called cubes. And from those data cubes, I now can start to perform my information analysis and actual development of knowledge with insight. This diagram shows us the typical path of information flow from a web client who is accessing ultimately through a web server information that is stored inside a database. And so these are all these points are opportunities for a bad guy to perform some malicious acts on the hopeful violation of your confidentiality, integrity, or availability of this valuable information asset. So we have the web client who makes a request, an HTTP GET from the web server. That port 80 traffic, or if it's SSL, that would be port 443 traffic, flows through the firewall. The web server now is the portal, and it communicates with an application server. That application server actually has connections back to the database, so that each of those stages, there is the opportunity for a bad guy to somehow violate the CIA, confidentiality, integrity, or availability of your valuable information assets. We have to recognize these so that we can defend against these. This diagram shows us how to interpret a URL. The question marks and the equal signs and the ampersands all string together that identify specific components of information that I'm actually querying for. And again, here's another diagram showing additional areas where a bad guy will attempt to violate CIA of this valuable information asset. We have URL attacks, we have input validation attacks, probably the most common, and then we have SQL injection or SQL query attacks. These are other forms of attacks on database applications. So in this section, we're going to take data mining to a slightly higher level. And we're going to move towards online transaction processing, or OLTP, and then we're going to look at knowledge management. And this is actually the development of data into information, into knowledge, and ideally into the highest level called wisdom. Online transaction processing implies real-time processing of transactions. Basically, that's what we're talking about. Is as a transaction occurs, the moment it occurs, within typically a few milliseconds, it hits the database and is actually processed. And so this is one of the later technologies, one of the more current technologies, and it is usable in the more time-critical applications and also used in e-commerce. As we compare transactional online transaction systems with data warehouse systems, the concepts are more immediacy on the OLTP transactions versus in a data warehouse where we have days or weeks to analyze and process information. Here with the online transaction systems, it is, like I indicated, very often milliseconds. Small amounts of data, very limited, very controlled, very refined processes, but very quick reactions. So a couple of issues related to online transaction processing is concurrency controls. Typically we have multiple users accessing the same data set, and what we have to do is implement some of those concurrency controls we talked about in the last section that lock records so that two users can't be modifying the same data set at the same time. We also implement the transaction processing with the begin transaction, end transaction, and if I don't reach that end transaction statement in a reasonable amount of time, all transactions roll back out, the all or nothing of atomicity. And we also need to detect or maintain records of these transactions, permanent records, not just record the transaction while it's happening and then we can throw that away. We actually record this for disaster recovery, and also sometimes it's used for regulatory compliance issues. online analytical process takes it a bit deeper. Here is where we're looking at this very dynamic data of OLTP, and we're actually analyzing it and trying to reach the same kind of conclusions that we would do in a data mining instance with data warehousing, only this is generally considered to be a little more quicker reaction, a little more dynamic in its nature. And the concept of knowledge management deals with elevating the value of your data by considering that we have data, but we put it in a certain context. This brings us to a level of information. And as I have information and I apply meaning to that information, it gives me knowledge. And when I have knowledge and I apply insight to the knowledge, it takes me to a level of wisdom. So my objective is to elevate the value of my data by adding more and more capability, more and more thought into the analysis of this data, and this develops this true knowledge base and knowledge management. Typically, knowledge management requires people, that's the end users that are actually needing the information, putting together the relationships in the databases so that we can begin to define and refine more of what we're trying to learn about this information. It then, of course, the information is stored on technological devices, computer systems with analysis engines and things along these lines. And those analysis engines, of course, are the processes that are going to be used to analyze the information, actually implement the data mining to produce the metadata, which we, of course, elevate to the higher and higher levels. This diagram is actually a sort of a reasoning flow chart. And it is a way that a knowledge base might be structured. It's quite complex to look at it, but as you look at some of these relationships, you begin to recognize that over on the very left-hand part of this, we have something called skill inventory. And it's a byproduct of an individual's education, and whether that's high school or college or graduate school, etc. And then also part of that skill inventory, we have specific skills. Perhaps this guy might be a welder or a database programmer or something along these lines. So we now will look at the how long they've been doing this, and do they have any specialized skills? Is it this language or multiple languages, things along these lines. So this is more of an analysis and reasoning tree that a knowledge base might utilize to try and build new relationships for analytical purposes. So knowledge discovery of information within databases is generally a refined, higher level version of data mining. Remember, data mining we generally think of in a data mart, a subset of a data warehouse. And this is more long-term, and generally I kind of see this as a little less sophisticated than actually this knowledge discovery process. So knowledge discovery I kind of see as a little more sophisticated, a little more refined. But they're both in the same vein. They both are headed in the same direction, to increase or elevate the value of your data and turn it into more and more useful information. So again, data mining, the objective of data mining is to take these unrelated details, aggregate them together, and discover these hidden facts or conclusions that we can reach, this metadata that we can derive from analyzing the information in ways that hadn't originally been considered. Generally, there are three approaches to knowledge management. We have probabilistic, how likely is it to happen. We have statistical, this is generally based on rules and specific one-to-one relationships. And then we have classifications, different groups of types of data, and looking at the relationships that they have, how close a relationship or how distant a relationship is this. So again, three different types: probabilistic, statistical, and classification approaches to knowledge management. Now, as we approach this knowledge base or this knowledge management, this high-level data mining, we get involved in more and more of the artificial intelligence systems. That's what we're approaching. One of those artificial intelligence systems is called the expert system. Now, the expert system is a particular type of artificial intelligence where we survey experts in a given field. And we survey by asking if-then type of questions. If, for example, a patient presents to a physician The combination of symptoms, scratchy eyes, runny nose, and a headache, what would be your conclusion? If this, then what? And by surveying many experts in a given field, we now can begin to define rules and relationships. If these 4 symptoms occur, that's the conclusion. If these 3 symptoms occur, that's the conclusion. So we build these if-then statements, and now we can implement the expert system. A classic example is the online nurse, where you go to our website, you check 3 or 4 boxes that represent your symptoms that you're presenting, and then you hit the go button, and what happens is they'll tell you you have a cold and you should lay down and go to bed and take 2 aspirin and drink plenty of fluids, things along these lines. With this collection of symptoms, this is probably what's going on. So that's a classic example of the expert system in use. Again, the expert system uses this rule-based programming, this if-then logic, as I described. And from that if-then logic, we use an inference engine to identify that you have this particular medical problem or diagnosis, for example. This particular conclusion is arrived at. Another form of an artificial intelligence system is called the artificial neural network. Now, this is where they take computers and they implement a computer architecture. This is a combination of hardware and software, perhaps many, many computers, and they try to simulate or mimic the human neurons in the human brain. This artificial neural network actually has the ability to learn from experience and from scenarios. Now, the problem is, how do you take 400 computers on a roller coaster ride to expose the artificial neural network to the experience of a roller coaster ride? That's where one of the bigger problems comes in with this artificial neural network. It's how do we present the experience to the artificial neural network so that it can actually learn from this experience? The problem is, or typically the approach is, some human has ridden a roller coaster, and based on that human's perceptions, filter number 1, that human will then input filter number 2, his experience, into the artificial neural network. So it's difficult to teach or to expose this artificial neural network to these experiences so that it could derive its own learning experience from the event. So again, the whole point of this knowledge management is to take data and increase its value by converting it into information, knowledge, and potentially even wisdom as we apply more and more context and relevance to the actual data set. That's the goal, is to continually refine and develop this data into more valuable knowledge. This chart shows us a summary of how we go from data to information to knowledge, and how this affords us higher level of solutions and more types of information that we can ascertain from this same original data set. We just refine it and develop it and massage it, and before you know it, we have something of real value. Now we're going to look at software development processes and models. We're going to look at the software development life cycle, and we're going to discuss individual phases briefly, but the major conception here, or the major concept you need to understand about this, is what the order is, number 1, but second, every stage must be permeated with security consideration. Don't do anything unless you're thinking about security. It has to permeate every single step of the software development life cycle. So here is the list of steps in the software development life cycle. You should know these steps and their proper order. It's relatively intuitive, so it's not like anything you're going to have to memorize and it's going to be painful. It makes sense. So if you look through this, first we have project initiation. This is where somebody has a bright idea. We think we can make some money at it. What do you say we give it a shot? Then we bump into functional design analysis and planning. This is where, if you have any areas of technical uncertainty, this is where you do your prototyping. And you would identify that, yeah, we can do this. The sticky parts, I built the prototypes, they all work. Now we just have to do the easy part and build it around that. And that's where we'll lay down our plan, and we'll specify how and who and when we're going to get this project done. Then we're going to firm that up with a little more detail, and we're going to actually design the system specifications. Once that spec is defined, then we move into the development stage. That's where we actually begin the formal coding. That will be the end resulting program, the software product that we're looking for. Once we get that coding done, we run into a phase that's kind of a loop. This is where we're going to install it on a few machines, and we're going to test it and evaluate it, and then loop back and refine it and test it and evaluate, and then we're going to loop back and we're going to keep refining, testing, and evaluating until we get it the way we want it. And then we're going to actually be ready to deploy. That's where we move into the operational and maintenance phases. Now that's the real lifetime of the product right there. And so the maintenance would be the patching and subtle upgrades. You know, this button should be bigger. It should have a red stop sign on it, and it should be located closer to this particular feature. So that's the kind of the maintenance phase of it. And then finally, we will end of life the product with the product's disposal. This is where we're going from version 2 to version 3, and we're no longer supporting version 2. That would be the disposal of version 2. Now, kicker here is, while we just walked through those stages of the software development life cycle, we have to understand that at each and every phase, security must be considered. We have to consider and implement security at each of those phases. So when you bump into a question that says which phase of the software development lifecycle should you implement security, should you first implement security, it would be at whichever one chronologically is first, because security should permeate every single phase. Now here, the main part of this slide has to do with that bottom bullet. We talk about the system lifecycle. System is actually a little bit more perhaps than the software itself. It's more of the entire computer or collection of computers or other machines and devices or people or processes that are involved in this thing that the software is aiding. So that's the system life cycle. But the bottom bullet talks about the system development life cycle. That's just the initial stage until we reach the operational and maintenance stage. And that's the development part of it. After that, once we get to the operational and maintenance stage, now we're in the real lifespan of the product, and that is when we roll into the system life cycle versus the system development life cycle. So that would be the line of distinction you need to understand about this slide. Here we're going to, again, go through these very quickly. Project initiation, where we figure out what we're going to do and how we're going to do it. Functional analysis and planning. This is where we're going to do our prototyping for anything we're not certain about. We're going to make sure that this all kind of aligns. It's a good project, and we're going to move forward. Then we're actually going to firm up that design specification. Very tight, very formal specification. Then we're going to release that specification to the developers, the guys who are actually writing the code, and that's the software development. Then we move into the installation, test, and implementation. Now this is just before we're going to release this product to the end user. So this is kind of a loop here where we're installing, we're testing, we're evaluating, and we might be refining the software a little bit, in, test and evaluate, and so there's a little bit of a loop there. Those first 5 phases deal with the development life cycle, software development life cycle. After this stage, when we roll here, we're now looking at the life of the product. This is the functional life, where we're in the operational and maintenance mode. This is hopefully several years of worthy use of this product, and then eventually we'll end of life at the disposal. Now, what you should have noticed here is at each of these stages, and feel free to roll back and look at those, we should be considering security at each and every phase. And here is a diagram that shows us some of the aspects that we might be looking at, perhaps even should be looking at, regarding security at each of these phases of the system life cycle. And here is yet another slide that identifies at each of the phases. Now this one limits us to only the software development life cycle. Actually, it continues on. It also includes the operational and disposition components. So this one actually is the system life cycle, and then the security considerations on the lower half that we should be evaluating, looking at, and ensuring security about or for in each of those stages. Now that software product requires a great deal of testing. We'll be testing small subsets of the program. This is referred to as unit testing. So I have one chunk of code that I have just finished. I'll perform unit testing on that one chunk of code. But then I'll integrate that piece of code with 10 other pieces of code, and I'll implement what's now called integration testing to make sure that these components work together and that we haven't introduced any security vulnerabilities as I integrate these. They may test out discreetly and remain secure, but as I integrate them, this is the opportunity for a bad guy to perform some form of attack. So I need to do this integration testing as I couple these modules together. Now, once I get the entire product completed, I need to present this product to the customer, the end user, and they may have a formal acceptance testing because they wrote a spec and they said, this is what we want that product to do. And now they're going to go validate that the software that I've provided to them satisfies their requirements. So the end user will perform the acceptance testing on the finished product. And finally, if and when I need to make modifications to the software product, I've implemented a change, different code, I should implement another round of testing to ensure security because these changes very often open up security vulnerabilities. This is referred to as regression testing. This slide identifies higher level testing and very specific testing. So I have more abstract levels of testing and very defined, very discrete component level testing as I go from the higher level down to the lower levels. But again, what does it say? It says we should be considering security and performing testing at each and every stage of the software lifecycle. I also need to be concerned about the I/O part of this, the security, the trusted path between my input devices and the system and the output devices, whatever they may be. I need to ensure that we have trusted path here. And so we'll implement things such as error detection and correction, message digest. These are hash values if I want to validate that a piece of code or a message has not been modified, things along these lines. So these are the types of controls that I will implement in this system, not just the program, but actually from the user at the keyboard all the way to the printed report, the input and the output components, to ensure that my data does not get contaminated or corrupted in any way. Again, this would be a violation potentially of integrity or confidentiality. Actually, it could even include availability. If somehow the bad guy was able to delete your print jobs, then the printed report doesn't exist. So as a result, we have a violation of availability. So some consideration relative to how should we test the system. Well, we've got this completed system done now. The way we want to test it is we want to input all sorts of data. If I have a telephone number field in a database, how about I type my street address in there and see if it'll take it? So violate the rules. The expectation is that's supposed to be, for example, a telephone number. Suppose I put a city in there. Suppose I put some command to format the hard drive. What happens? All of this type of stuff should be tried. So don't just provide the expected data. You have to provide the unexpected data. Further, let's see, we need to validate the information before it's being processed. Now that's done during the development part of this. This is where our data validation on all inputs should be programmatically ensured. This is not an after-the-fact testing component, but we have to validate that these checks have already been put in place. That's what I was describing when I tried to put a command into a field that should only take number values. Why would it take format space C:? Why would it take that command? It should reject that command because it's expecting a telephone number. Some other areas of security that we want to consider on this system that we're talking about is the potential for object reuse. And this is these are things like, suppose we have tape disks, tape components that we're using to input and output data from. If I'm reusing these, is it possible that some previous write on this tape somehow interferes or is able to be read when it really wasn't my intention that that information be available? I thought I deleted that kind of concept. Then there's garbage collection. Again, this is purging all data out of memory and other writable media. Once we're done working with that data, we want to be sure that all that information has been fully removed before we allow new processes to inhabit that same memory area. And then something I had mentioned earlier has to do with the maintenance hook. And again, this is willfully and for good purpose inserted backdoor. The developer didn't want to have to go through all the steps of logging in and moving into this particular region of code. So what he does is he builds a backdoor so that he can just go right to this spot and do his refinement, evaluation, and refining of his software. So that's built in on purpose, for good purpose, but they have to be pulled out before we release the product. Maintenance hooks should all be removed before the product is ever released to the end user. Two definitions here that you have to be very clear about: verification versus validation. Remember how we wrote that very formal spec about this is the product that we're going to define or that we're going to build, and then we hand that specification to the actual developer, the guy that's going to write the code. When we confirm that the code he wrote matches that spec, that is called verification. What we're asking is, did we build the product that we specified? That's verification. Validation, on the other hand, is when we finish the product and we go to market this product commercially, does it sell well? Does it solve the end user's goals? Does it satisfy their objectives? That is validation. So verification says, did we build the right product? Validation says, verification says, did we build the product to our own specification correctly? Validation says, did we build the right product, the product that the end user needed? So now we're looking at this final product, and there are two areas of assurance that we want to evaluate. Now let's put this in mind, put this in perspective. We have functionality, and then we have assurance. Functionality says I can do it at least once. Assurance says I can do it that way every single time. So we have operational assurance, and then we have life cycle assurance. Operational assurance basically provides a basic level of assurance that the system has satisfied the security objectives following our security policy and our security requirements for this particular product. Whereas life cycle assurance also carries on into the, not just the development stages, but carries on into the operational and disposal stages of that product's life. So it's the bigger picture. The life cycle is the bigger picture versus the operational is more from the development standpoint. Did we develop it correctly? Life cycle says, and can we maintain it correctly? Now the change control process is very, very similar to the software development life cycle. If you think about it, these are virtually identical. It's basically the difference between a brand new product versus a brand new idea that is coincidentally modifying a product. So the steps are approximately identical, and the concept of security remains intact. Security at every single phase of the process. Now, there's a couple other details that go along with change control, and that is that we have a more rigid demand for documentation, approval, and of course, we should always be retesting for security 100% after we make any change. So the change control process is just like the software development lifecycle, with a little extra enhancement on approval, formal documentation, and added security beyond security at every facet. We have to be looking at things a second time because now we've modified the way they work. We tested them once. They were secure. Now we've modified that. We have to test it a second time. In addition to that, we need to separate the duties relative to this change control process. This would be where one of our production workers is buddies with one of our software developers, and he just doesn't like the fact that he has to log in every day. It takes so long, and besides, he forgets his password, one day a week, and it's a problem for him. So if we could just get a cut of the software that didn't have that password thing in it, that would be great. So what we want to do is we want to separate those duties so that it isn't one guy that could do both of those. It's actually two different people, and we actually have boundaries up so that production doesn't directly interface with our software development team. So again, controlling how changes take place, the change control process. Again, as we have a product in place, there's always going to be the need for improvement or change or refinement or integration into some other component, or some other component needs to integrate into this, or whatever. There's always going to need to be changes made to this program. We have to do this in a very controlled fashion. Formal procedures, formal approval, formal documentation, and security at every single step. Bottom bullet is a fine bullet. Ensure that the product security policy is still being enforced even after the changes have been implemented. And as we look down the list of steps here, what we'll recognize is we could marry this almost completely with the software development lifecycle. These steps are approximately the same. What you're going to see here, though, is a little more emphasis on formal approvals and formal documentation. But remember, security permeates every single step. And the steps continue on here until we finally make the version changes and report that the changes have been completed, and we make that report to senior management. Now here's where we were describing that thing earlier relative to separation of duties. We can't have the guy who wrote the program running the machine that the program is on, because he's the guy who has the skill, the motivation, and the opportunity to modify the program and violate the security controls or the access controls. So that would be too much authority for one individual. We need to separate the developers from the guys who are actually using the program, the operators, or the end users. So they should be separate functions. In addition to separating those functions, we should have a completely separate entity performing the quality assurance. This is oversight, this is validation that these two haven't gone into collusion. Why? Because this third guy is now verifying that the program that the guy is running is actually the one that we specified, the one with all the security features, the logons, the access controls. So again, quality assurance department is yet a third discrete role that should be in place on any program where we're developing software for our own internal uses. In addition, here we finally mention a software librarian. Now this is a single person or perhaps even a department in the organization that is the sole source of software for the organization. Your developers write the software. When they formalize it and release it formally, they release it not to production, they release it to the library. The librarian then will formally deploy and roll out. Very often the librarian is used for commercially acquired software as well, because this is a choke point. This is a way to funnel or channel all software that is being deployed in our environment so that we can assure we have that we're remaining accurate with our licenses. This is another area of the CISSP that is a priority, and that is we have to ensure that we are not violating our software licenses. This could be a vulnerability if we are using 100 copies of Microsoft Office when we've only really paid for 4. If Microsoft finds out about this, they could sue us, they can fine us. There's all sorts of problems that they could introduce into the company. So this librarian it's another place where we not only store our media for our commercial software, it's the release point for all our internally produced software. It's also a great location to maintain our software licensing and licensing controls so that we can keep a handle on that as well. Next, we're going to take a look at web security. Now this is a relatively new addition to the CISSP exam, so this is probably new information. You want to take a careful look at this and be sure you understand the concepts that go along with the slides that we're presenting here. Let's start with a typical example of how information should flow relative to a web client connecting in to a web server and accessing information. On the left, we see a user who's using a browser who's connected up to the internet and has input the URL for your web server, for example. And so it goes through a routed network. Ultimately, it goes through a firewall and then attaches to what we would consider the demilitarized zone, or the DMZ, for your publicly exposed web services servers. That would be your web server, your FTP server, your email server, things like this. Generally, again, protected by a firewall between the internet and your DMZ. So we see bidirectional information flowing from the client through the firewall into the DMZ where your web server is. And if we follow the green line on this diagram, it goes to a single mirrored web server. So all three of those servers have the same exact content. It's just this query, because of load balancing issues, wound up on the extreme right web server. Now the client's query hits that web server, and that's where the client's connectivity should stop. You see the red circle with the line drawn through it just below that web server. That says that the client's connection has stopped at that point. It is not allowed past that web server. The web server itself has a connection back to the data store through the application server and into the data store. That's a web server communicating with its own support services, not the client connection. So in that case, that is an impersonation is what's happening there at the web server. The web server has that inbound connection from a true legitimate client, but then the web server impersonates a user. And it's through that user account and the privilege granted to that user account, and only that user account, that a connection can be made through the application server and actually query the database where the data store resides. The thing to remember here is that there are vulnerabilities throughout the entire system. And while we protect 99 out of 115 of them, the bad guy only has to find one of those extra ones that we haven't protected, and boom, he owns the whole system. All it takes is one unlocked door, and the entire system can go down. We've identified this already a time or two, but let's walk through it again. Particularly the diagram on the right-hand side of the slide shows that we have our database, our data store off to the right, and that is isolated from the application part, the actual part of the system that is going to query the data set. So I have a data set, and then I have an application server, again, for isolation and as a element in the tier. And then beyond that, I have the presentation services. That's the service that is publicly exposed, and that's the service that connects to the client side. So those are the four stages. Client connects to presentation, presentation connects to application, application connects to data store. That's generally the proper approach. I would have a firewall between client and presentation, and another firewall between presentation and application and data store. So generally I would have at least two firewalls in this tiered approach. Again, we see these layers of isolation and security. The client would actually live at the top of this screen and would make a connection into the publicly exposed web servers. Those publicly exposed web servers make a connection back through another firewall, impersonating a trusted user now, not the anonymous user or the end user, the client out on the public internet, but this is now an impersonation of someone who is trusted, and that trusted user account has enough privilege to launch the application, which now can massage the data set down below. The difference between these two diagrams is the diagram on the left is identifying to you the infrastructure, whereas the diagram on the right identifies to you the services that are provided by that infrastructure. So they're kind of like, it's the same picture, only two different dimensions. One has to do with the actual device level, the other has to do with the service level. There is a great deal of sensitive information that can be ascertained as clients are connected up through web servers and accessing information behind those web servers. Some of those include credentials that may be stored in cookies or in ASP pages. Now, typically when a cookie stores credentials, if the company, the website that produced that credential is diligent and paying attention and doesn't want to get sued, they will encrypt the cookie, but very often they're looking for fast and dirty encryption, just enough to hide it so that they can feel good about it and not be negligent. But the bottom line is the encryption technologies that they use very often are more for ease of implementation and performance rather than real secure. So as a result, they're crackable. Even if they're encrypted, if there are credentials in those cookies, very often it is very easy to decipher or decrypt those cookies and gain actual usernames and passwords, credit card information, things along those lines. Now, on the server side, the HTML content itself, the actual web page, the script that produces the web page, very often has sensitive information. And if you've ever gone into a browser and said view source on the menu item, what you'll see is the actual HTML code, the ASCII code that produces that web page. If you peruse through that, what you'll very often be able to identify is actual names of servers and sometimes even usernames and passwords so that the web page can make a connection using an impersonated account. Remember the impersonation process I described earlier. And very often this information that the guy who wrote it thinks is hidden is readily available to anybody who connects up to that web page. Now this is one of those passive scanning tools, or I'm sorry, passive recon tools, is if your target has a website, browse the website and view the source. And very often a bad guy can learn a great deal of what would be considered sensitive information just by looking at that source code in the HTML pages. If we can get to the client computer, we can look in the client's browser cache, the client's browser history, or we can peruse through the cookies on that client computer. And that means whether I'm standing there at the console, locally on that computer, or whether I can connect into that computer and peruse this information remotely, that information is readily available. So this type of information should typically be purged on a fairly regular basis because very often it contains sensitive information. And then the last one here says web server error pages. Now, this is a technique that is used in one of the many attacks called cross-site scripting. This is where a bad guy tricks the client into clicking on a hyperlink. Typically, he'll do this on a web page, or he'll send an email that has a hyperlink built into it, and he'll try to convince the victim into clicking on this hyperlink. Now, that hyperlink actually doesn't go to www.gatorade.com or some other standard, viable, legitimate website. Actually, what happens in the background, the hyperlink portion of itself, the code that is the link, the bad guy has actually written malicious code on the extension of the URL. And so when the victim clicks on this hyperlink that has this malicious code attached to it, when the client does connect up to the legitimate web server, this malicious code is received by the web server. The web server doesn't understand what that information is, will regurgitate that code back in the form of an error message and submit it back to the sender, the victim. Well, the way the victim's browser very often will interpret this message coming back from the web server is he thinks he's supposed to process this, and as a result, he's actually executing the malicious code. This is the way a cross-site scripting attack works. Now, that is one area where web server error pages produces a vulnerability to a victim. Another area is on the web server itself. If a bad guy or anybody asks for, let's say, a web page that doesn't exist, the web server automatically generates an error page. Well, very often that error page says, I'm a Windows Server 2003 server with Service Pack 1, and that's too much information already. We already know too much about this box. Stop telling the bad guy too much information about the nature of your system. You're giving him insights as to how to break into this machine. So your error pages for your web server should all be sanitized so that there's no sensitive information or no details about the technology that is your web server. Those should be sanitized so that there's just generic information that says this page doesn't exist, try again, something like that. So cookies. We've mentioned cookies a time or two. A cookie is a file that is written to the client's hard drive. There's a folder called Windows Cookies on a Microsoft machine, and inside that folder, for every website that you connect up to, if they choose to, by a script that runs on the server, they will actually record what happened while you were here at the website, and they will write that back to a file on this in this folder, this cookies folder. This is referred to as a cookie. Sometimes that contains sensitive information about the client session. It might be username and password, it might be credit card information, it might even be just a telephone number or a home address. That's too much information. So these cookies can be dangerous. Now, they're there for good purpose, to enrich your experience on the website. So we don't necessarily want to turn them off completely, but we do want to restrict their use, and we want to purge them on a fairly regular basis. There are two main types of cookies. We have persistent cookies that stay on the computer even after you've left the website, and then we have session cookies. Now, when you connect up to a website, and let's say you're walking through an e-commerce website and you're picking out product that you want to buy, and you say, give me one of those and two of those. The fact that you're selecting these components that you want to buy, this gets written into a session cookie. And then when you hit the checkout stand and you actually submit your credit card over an SSL tunnel, things along these lines, and you actually execute your sale, that session cookie should be deleted from your hard drive. That's the nature of a session cookie. When the session is over, delete the cookie so no information, residual information, remains available in the cookies. However, not all websites want to purge their cookies. They want to remember you the next time you come back. They also want to know what you purchased so that they can now tell you about this new model that's on sale or some other supporting product that you might be interested in. So very often, they don't want to purge those cookies. They'll make them persistent. And as a result, this file lives for the lifetime of the computer. Periodically, you might want to just purge those persistent cookies. Now remember, these cookies are there to give you feature-rich browsing experience. And as a result, if you purge your cookies, what happens is, let's imagine you had a Yahoo personalization page that was pink and had your horoscope up in the left-hand corner. Well, when you purge the cookie for this Yahoo personalization website, it no longer remembers you. It no longer knows that you want a pink background, and it no longer remembers that you want your horoscopes on the front page. So that's some of the stuff that you'll lose when you purge these cookies. But for security's sake, it's better if these cookies don't exist on your computer for the most part. Now, there's another facet of cookies that you need to understand, and that is first-party cookie and third-party cookies. When you go to www.gatorade.com and Gatorade writes a cookie to your computer, that is a first-party cookie because that's a cookie that's written to your computer by the entity that you were trying to connect to. But what happens very often is these websites trying to generate revenue will sell marketing services to other companies. What happens is when you go to, for example, and I don't mean to be beating up on Gatorade, but if you go to Gatorade.com, they may have sold your connection to 10 other companies. And for a penny per cookie, they'll write these 10 other cookies to your hard drive. These cookies now will monitor your browsing and report back to those 10 companies to tell those 10 companies what you do on the internet and how long you stay at each site and things along these lines. All sorts of information about your browsing habits and the types of products that you like and things along those lines. Those are referred to as third-party cookies. If they are not the actual desired site that you're going to and you still get a cookie, that is a third-party cookie. In most cases, you can turn off third-party cookies but allow first-party cookies. This is generally the more secure way to set things up. If you don't want cookies at all, you can usually turn off cookies altogether, first-party and third-party cookies. Another area of vulnerability regarding web surfing and web connections has to do with your browser cache. Your browser cache is another folder that lives on a hard drive of a computer that stores all of the files that are downloaded with each and every web page that you connect to. So you connect up to a web page, it might pull down 20 or 50 or even 100 files. Those files are written to the hard drive in this browser cache. And that way, if you pop back to this web page, we don't have to connect back up to the website and download them all over again over the internet. I just pull them up off the hard drive. I already have a copy of those files. So this browser cache can store all sorts of information about the websites you've been to, perhaps even some forms that you filled in on these websites, things along those lines. So the browser cache can also be a vulnerability, a source of providing sensitive information to a bad guy who might be perusing your system. This again has to do with viewing the content of an HTML page, the actual coding or the script itself that is the HTML page. There's a lot of information that might be stored on this page, and all you have to do is go to View Source, and you can actually look at this code. And it's amazing how much sensitive information you can learn about each and every one of these web pages. If you haven't done it before, you should take 10 or 15 minutes and look at it. And what this says is whoever's writing these HTML web pages should also be educated to the fact that they can't put sensitive data in these pages. Web server error pages, we discussed this already. We have standard server error pages. Very often it identifies the platform, the operating system, the patch status, things along these lines. That's too much information. I don't want to give that bad guy that easy and that clear a fingerprint of the nature of my server. So generally we want to sanitize these web server error pages. Now these web server error pages can also be used in something called a cross-site scripting attack, which I described a few moments ago. because there are many actual stages or steps in the process of a client connecting up to a website, that website connecting to an application server, that application server connecting to a backend database, and the authentication processes and the encryption processes and all the other processes that go on, there are many opportunities for a bad guy to find a single vulnerability in any one of those steps, and that's his attack point. So what we have to understand is what these various steps are, and that there are vulnerabilities at each step, and we have to consider the security of each and every one of those stages of the client browsing over the internet. Something else we want to do is we want to harden the server. We want to make this server less available to the attacker. We want to reduce the attack surface, is the phrase, reduce the attack surface of the web server. Some things we can do to help reduce the attack surface of the web server. First, remove all the software, not just administrative tools, but these are some of the more important ones. We want to remove 100% of the software from the server that isn't exactly required to run the services that that server is dedicated for. Now, these are on your publicly exposed web servers. Anything behind the second firewall, generally, I don't harden them to this level, generally. I still may consider it, but I don't necessarily have to knock them down this far. Anything publicly exposed, this should be a requirement. Knock down all the administration tools. Why? Because when a bad guy breaks in, he's going to use your administration tools to break your box. Don't give him those tools. If he can break in, make him find a way to upload tools so that now he can manipulate the box. Don't give him the tools. Further, we should reduce the number of user accounts that are authorized to manipulate this box. So always a minimum number of user accounts on these publicly exposed boxes. Also, if we've developed a custom software like our content for the web page or applications that interface between the web page itself and the application server, all of this software must be carefully scrutinized for vulnerabilities. And then, of course, CGI scripts have always been a vulnerability and have led to many attacks. A CGI script is a script that runs on the web server. With every inbound connection, this CGI script will launch and do the work that's in the script. Well, bad guys historically were able to break into these scripts, write their own instructions onto the CGI scripts, and now in addition to doing all the work you thought you were doing, you're doing the bad guy's work too. You're infecting all of your clients with malware, or you're allowing the bad guy to steal all the communications that are occurring between the client and your web server, things along these lines. Many bad things can be done with a CGI script. So here are some examples of some common web server flaws. Information disclosure, arbitrary code execution, denial of service attacks, profiling of the systems, and web server vulnerabilities of many natures, viruses, things along these lines. So these are all the types of attacks that can and will be thrown at your web server. In other words, always consider that this guy is publicly exposed. Always consider that he can and will be compromised. So we never want to put anything on that web server that we would consider valuable. We want to just have him be the portal, the front face of the website, but he doesn't actually hold any data. He has a connection back through the second firewall into the more sensitive information, but that we've secured in another fashion or in different fashions. Now the bad guy has to not just break into your web server, but he has to crack through those securing technologies as well. So again, consider that the web server is compromised 100% of the time. And again, one of the most prevalent forms of attack, the more successful attacks, the vast majority of them are all due to poor coding. And the largest of these is improper data validation. In other words, when somebody's supposed to type in a telephone number in a field, the programmer, the guy who wrote the code that designed that field, should also say it should not be any more than 10 characters, and it should never include alpha characters. It's a phone number. But the problem is the program developers have never been trained that they're supposed to do this. Why? What are the rules? Make it work and get it done fast. Well, this is extra work. And it works without this. But what it does do is it lets the bad guy break in. So proper data validation for 100% of any user input should be provided. By the way, that includes the URL itself. That includes the web server accepting a URL which says, take me to this folder and launch that page, and then do this thing, this extra thing, which might be malicious code. That should all be truncated. That should all be rejected. Probably I should give the guy an error message that's been sanitized and not provide any further response until he gives me a URL that is legitimate, that doesn't contain that extra garbage. I'm not even going to tell him anything. I'm not going to give him any messages. We also see Unicode attacks, directory traversal, buffer overflows, probably the single most prevalent, and again, sensitive to this data validation. Cross-site scripting, I've described a time or two, SQL injections, and then the way to crack out of the service and into the server. SQL injection, that's what it does. It's a syntax that actually breaks out of the SQL application and breaks into the SQL server. So anyhow, we're going to look at these in more detail. First is the URL itself, and as I described, a URL should say https:// fully qualified domain name / virtual directory / web page. And if it contains more crap than that, it's probably a malicious attempt. So what typically is done is there's a standard set of filters that look for that malicious code, and it filters out that malicious code. The problem is, because of different languages and different character sets, there is something called Unicode. Unicode is, we take the uppercase US English letter A, and we have to somehow translate that into the Russian Cyrillic character, and so there's a single code that represents our A and the Russian equivalent of our uppercase A. Well, the bad guy can now turn his malicious code into this Unicode, and the filters very often aren't that thorough. They're looking for the actual code, the actual letter itself, not the Unicode translation. So a bad guy very often can slip past your filters for malicious code in the URL by translating their malicious code into Unicode. Unicode, as you can see from the slide, is generally a representation of a %, 2 digits in hexadecimal, %, 2 digits in hexadecimal. So the one we see here in the slide says %C0, %AF. That's a / in Unicode. And if we're filtering for // after the URL is over, that would be a beginning of an attack, by the way. We might filter for that /, but our filter isn't looking for the COAF. And as a result, the bad guy can send a COAF. It bypasses your filter because it's not the /, but the web server service says, oh, that's a Unicode, and he translates it into a / and then lets the malicious code run. So this is a Unicode attack. Here we see the directory traversal attack, and it actually takes advantage of the Unicode attack that we were just describing. Directory traversal says, while I'm connected up to the web server, and it's at http://website /scripts / blah blah blah, he's now going to inject Unicode to bypass your filter, and then what he's going to try to do is he's going to try to crack out of the scripts folder in the bottom bullet example there, and he's going to try to crack into the system32 folder where a locally executed executable resides. He's going to try to launch that executable and have it respond back to his machine, giving him a directory of the inetpub folder on this computer. So this is a directory traversal attack, and it takes advantage of Unicode, as you see right there in the middle, the COAF, that bottom bullet. So this is the type of attack that is done in a URL. It takes advantage of Unicode, and it is a directory traversal attack. This is a sample of a buffer overflow. This is where the guy who wrote the form that was expecting user input did not validate the user input. And as a result, he let the bad guy send a whole bunch of garbage. He was expecting 8 characters. He got back 800 characters. And in that 800 characters was some malicious code and a redirected pointer. We're going to look at a buffer overflow in a few minutes, but we're going to understand how this actually works. In other words, we feed so much information into the system that I've overwritten the legitimate program, and I'm now going to have your computer run my malicious program. That's what a buffer overflow does. The desire by the bad guy is to take control of this web server, get this server to respond back to me with my command prompt or with a backdoor that allows me to break into the server. so that I can take over the server. And here's a cross-site scripting attack. We've discussed this a time or two. I'll run through it quickly again. What we do is we trick a victim into clicking on a hyperlink. Generally, this is done using a phishing attack spelled with a PH, P-H-I-S-H-I-N-G. That's an email that has a hyperlink embedded into the email. And I try to convince the guy, come to my website because we're going to give you free widgets, or you need to validate your account, or you've just inherited $1,000, or any stupid scam, trying to get the guy to click on that hyperlink. Well, that hyperlink might appear to be a legitimate website, and it might be true that in its appearance it's a legitimate website, but the link behind that actually makes it the hyperlink actually doesn't go to that website that is presented in copy in the phishing attack. It's actually embedded code, and it is going to send malicious code as an extension to a legitimate URL. So it's going to say, go to this server and feed him this variable. Well, that server isn't expecting that variable. So when when the victim clicks on that hyperlink and it sends all this garbage, malicious code, to the target server, the target server looks at this malicious code, says, I don't know what that stuff is, and it generates an error message and sends it back to the victim. The victim's computer receives this error message, isn't quite sure what to do with it, so it attempts to process this as an executable. And now what we've just had accomplished is the client's browser has just executed the malicious code. This is an example of a cross-site scripting attack. Now, cross-site scripting attacks are very, very numerous. It's a whole wide range of different types of attack. This was just one example of how a cross-site scripting attack can be performed. Another common attack is the SQL injection attack. Again, this is where a bad guy is working on an application, connected up through the internet, of course, to a website that is running a SQL application. If he can identify this as a SQL server, he can try this SQL injection attack. And what he's going to do is he is going to type into a field, user field, that should be for a phone number. He's going to type in 300 characters, for example, and part of that data string that should only be a telephone number is going to be code that is designed to break out of the SQL application and into the server itself. So I'm going to break out of the app and break into the server with this SQL injection. That's generally the objective of a SQL injection attack. So again, if the guy who wrote this SQL database, this application, had performed data input validation that this phone number is a phone number, it's 10 characters, it's numeric, it's never going to contain alpha characters, anything but 10 numeric values discard, the attacker would never have the opportunity to perform the SQL injection. See, these types of attacks are 100% preventable if the software developers would simply validate all user input. But they don't. It takes too much time, and it doesn't have anything to do with functionality or getting it done fast. Misconfiguration of the website. Well, if the website is configured to allow something called directory browsing, and that's what this particular setting does. Directory browsing says, instead of showing the HTML presentation, you know, the colored background and the little flashy banners and the buttons and the icons and all the graphics and stuff, just present the folder very similar to an FTP folder, make it available for download. And this is one type of misconfiguration attack where we allow directory browsing. And if directory browsing is turned on, then the files are presented for just discrete download, and you can simply copy them to any folder you care to on your hard drive and then peruse them later. And sometimes some of the files are perhaps a user database. Now I can start to crack into this user database that I've been allowed to download. And here's an example of what that might look like. As we see in the center picture here, that would be what is presented when directory browsing is turned on and I approach the website as if I'm trying to look for the file and not the HTML presentation. CGI scripts, Common Gateway Interface scripts. Again, Common Gateway Interface scripts are run server-side and are a script that gets executed with every inbound connection. And as a result, if a bad guy can break into this old CGI script that hasn't been protected properly, he can now modify that script and have it do whatever work he cares to have it do every time a client connects up to this website. So old CGI scripts, back in the old days, we didn't have these security concerns, and as a result we didn't go to the extra measure of securing them. And very often they did some very dumb things about writing these scripts, allowing bad guys to manipulate these scripts and do whatever work the bad guy wants to do. Something we should do on all of our publicly exposed systems is auditing. We should be taking as detailed logging and auditing as we possibly can enable. But by the way, just because I'm recording it doesn't mean it's doing me any good. I have to be monitoring those logs. That's the hardest part. We have to be looking at these logs and looking for anomalies, violations, bad things that are bad guys are trying to accomplish on our servers. This will teach us how we need to strengthen our security and defend against those attacks. We might also be able to identify IP address ranges, and we can now begin to block those IP address ranges so the bad guys can't get to us. Now, they can still get around them, but you know what? Every layer of security that we can put up, so much the better. We should be patching our publicly exposed web servers. By the way, we should be patching 100% of all of our computers, but more specifically and especially all of our publicly exposed servers. Why? These guys are under constant attack. 24/7, the bad guys are firing stuff at these servers. That's why you need to consider all of your publicly exposed servers have already been compromised. Don't put anything on those servers you don't want to lose. So again, the more we patch them, the more secure they should be. That's a general rule of thumb, and so we have to be very diligent about keeping these applications and operating systems patched to their fullest. So relative to securing your web services, Microsoft has a list of best practices, things that they recommend you should do. It starts with hardening your server and doing some of the things we've already discussed relative to firming up that box to reduce the attack surface and seeing to it that the bad guy can't get into the box. Further, it says you should lock down the resources with permissions, SharePoint permissions and NTFS permissions, and see to it that those permissions remain intact. If a bad guy can break in, he may loosen permissions so that he can get more access to more things. Build your system in that tiered approach. Remember, we have the data store on one set of boxes, we have the application running on a different set of boxes, then we have a firewall, then we have the presentation servers, those are the publicly exposed web servers, and then we have another firewall, and then we have the thin client, which is either the web browser or some application that's custom developed to interface with your web application. So build this isolation into your system to try and reduce again the attack surface for that system. Further, we want to strongly authenticate the users. You can use things such as digital certificates following the X.509 standard or the PKI standard. You can use multi-factor authentication. You can run authentication in an SSL tunnel. This is a component of the extensible authentication protocol. How we can first build an SSL tunnel, and then I can authenticate using CHAP, MS CHAP, digital certificates, biometrics, smart cards, swipe cards, any of these. But if I can introduce multi-factor authentication as a requirement, so much the better. Now on a web-based application that's usually a little more difficult, then I'm typically going to use a digital cert on the server side to use that to build an SSL tunnel, and then through the SSL tunnel I can strongly authenticate the client with MS CHAP or MS CHAP v2, or perhaps a digital certificate. That's even better. Further, any communications that are flowing between my web server and that client, I want to have in an SSL tunnel. SSL is Secure Sockets Layer. Again, it requires a digital cert at least on the server side. Could use a digital cert on the client side. These are strong authentication mechanisms. Further, from the web server back through the firewall to the application server, and then application server to database server, I could build an a VPN tunnel between those points so that if a bad guy were somehow just to be able to connect up to the DMZ, the segment itself, all he would see would be encrypted traffic, and he still would not get access to any of my sensitive information. So protect the traffic with SSL tunnels or VPNs. And finally, we need to maintain the server. We need to see to it that it's patched properly, that we have auditing enabled, and all the things that we've talked about there. So we need to see to it that the server's operating system is at its strongest possible point. We also should protect the server physically. In other words, have those servers physically isolated so that somebody in the office perhaps might not just walk by and disable some security feature. We want to have them in a secured room where authentication is required before they're even allowed to physically touch those web servers. So some common mistakes that are made relative to these web-based applications: providing too much information. We leave the administrative tools and other applications available on the server. We also have services that are available and running on the server that are not required. Disable and turn those services off. We have weak or flawed authentication. Sometimes we may even have no authentication whatsoever. Configuration management means we need to be sure that the configuration, the security structure of the box hasn't been tampered with. See, what a bad guy will do is if he can break in a little bit into the box, he's going to try to break down some of your security mechanisms so now he gets easier access. Or perhaps he's going to turn off the detective mechanisms that will identify him and alert you. So he's going to try to turn those, like your intrusion detection system. He's going to say, yeah, friendly traffic is anything that comes from me. So don't recognize this as an attack or a threat. And now all of a sudden your IDS isn't reporting when this bad guy is throwing all sorts of exploits at your servers. Data validation on the software development side of this. Every time you expect a user to provide information that's going to contact one of your servers or any of your applications, that information must be validated. If it doesn't look exactly like what you're looking for, if it doesn't look like a URL, it doesn't look like a phone number, throw it away. Or truncate it. Knock it down to, if the field is 10 characters long, knock down everything from character 11 on. Just throw them away. And now the bad guy can't get his malicious code into your system. Sequence numbering. This is a communication system from server to client. Now, as the dialogue continues on, these sequence numbers are identified between server and client. So the client is expecting a certain sequence number on the next frame back from the server. And if he doesn't see that sequence number on the next frame back, he throws that frame away and figures it's gotten corrupted. Same client to server. The server is expecting a certain sequence number on the frame coming back from the client. And if the server doesn't see that sequence number, the one he's expecting, he throws the frame away. Sometimes the patterns that are used for this sequence numbering scheme is very predictable. A bad guy figures it out, and now he can actually hijack a session by injecting his frames in, and he knows what sequence numbers, or he's guessing with an educated level, guessing what the sequence number is, and he's able to hijack the session. So what we need to do is use a much more convoluted sequence numbering scheme. A new protocol that came out that's called counter mode protocol. This can be implemented to very randomly, widely randomly generate these sequence numbers, so they're not very predictable. And then finally and lastly, logging should be turned on in all cases. So these are a list of common mistakes that occur on our web applications and web servers. Things that we should do to minimize our attack surface is never trust data coming in from a browser or any user input. Always validate that user input 100% of the time. So much of the attacks, so many of those attacks, so many vulnerabilities could be simply eliminated, reduced to zero, if we would simply validate all user input. But the programmers don't do it. Why? It takes too much time. It's never been part of the job. The job is make it work and get it done fast. That has to change. If they would only validate 100% of user input, they would knock the various attack vectors down to zero, eliminate them completely. If your software fails, it should fail in a secure fashion. Don't fail in a way that now your access controls are turned off. They should fail in a way that the access controls are not just still in place, but the system is probably even more secure. In other words, we actually shut down the database so no access can occur. Sensitive data should never be cached. We should have layer upon layer of security, as I described, the back-end server that's holding the data store, then the application server, then a firewall, then your DMZ with the presentation server, the web server itself, another firewall. And so layer upon layer, and then of course we have antivirus, anti-spyware, intrusion detection systems, et cetera, et cetera, et cetera. Harden the servers. And again, don't depend on security through obscurity. Obscurity is the weakest form of security. If they can't find me, they'll, they can't attack me. Well, you know what? They'll find you. So the simple thing, as simple as removing sensitive information out of your HTML code. A little commented statement that says, this part of the application connects to a server named Bobo, and it's this folder, and the username to get in is that, and the password that I'm using is this. Those comments in this HTML page, while we might think it's obscure, nobody's ever going to find it, people find it. All you have to do is hit View Source, and you can look at 100% of that content. So don't depend on security through obscurity. They will find you. Next, we're going to look at patch management. We've already talked about this to some extent, but we're going to flesh it out just a little bit further. We must be diligent in the patching of our operating systems and our applications. This is an ongoing thing. It can't be ignored. It can't be forgotten. We have to do it on a regular basis. Many of the newer operating systems and applications will automatically pull back, check back with the manufacturer, the vendor, and check to see if there are new updates. And then it'll either report to you that there are updates and allow you the option of manually installing them, or you can configure these very often to automatically install these patches. However that happens, patching should be one of these ongoing processes that simply cannot be forgotten about. This slide identifies several facets of this patch maintenance that we need to consider. First, that we have to have the infrastructure. There has to be a team or an individual assigned with the formal responsibility. It's your job to keep these boxes patched. So you set up the system you need and you see to it that it's happening. It isn't just turn the system on, it's then the maintenance and the monitoring of that to make sure that it's all working correctly. The second facet has to do with research. When we do hear about a patch, we need to understand that the patch is for us. It's relative to our system or our version of the application, whatever. And then we also have to validate that the patch has come from the actual legitimate source. Because the way a bad guy can infect your system and actually take over your system is he sends you a patch and it's got his malware tucked into it that opens up 10 new back doors. So it has to come from the trusted source. That's the research side of it. Before we deploy the patches, we should test them and evaluate. Does this patch conflict with any of my software or any of my hardware, any of my drivers? So I should always be pulling them down, evaluating them in a test environment, and only after they've passed sufficient testing would we plan the deployment. If we do accidentally deploy and then discover a problem, we should have a rollback routine or procedure in place. We should know how to do this. If I deploy a patch to 2,000 client computers and then discover it blows up our mission critical application, we've got a serious problem. I need a way to step back out of this problem spot. So have a mitigation plan in place. Then I need a deployment plan. Now, as I said, many of the newer applications and operating systems have an automated deployment routine where it connects up, it advises you that there's a patch, you pull it down, you test it, and it can automatically deploy. In other words, the box already has the software. You just have to push the go button to allow it to be installed. Other times what I need to do is actually push that software out through something like a group policy for software deployment or something along these lines. Well, somehow I have to see to it that all of the boxes that need this patch get the patch. And then, of course, I need to validate that it did get installed, it installed correctly, and that we keep a current log of the status of all the patches on all the boxes. And this way, if 10 boxes of my 100 can't get the patch because of some conflict, I'll know that. And later, when we're doing a survey and we say, hey, we're missing 10 patches over here, and you go to install it, boom, you just blew up your mission critical application. So I need to keep good records about exceptions, about when things got installed, and things along these lines. So validate that the deployment did occur, that the system seems to be running correctly, and then keep track of all that stuff so that you can maintain records and know what the status is and should be for each of these boxes. Now, some other issues related to patching. First, patches are software, and approximately 1% of all software has a bug. Therefore, the patches very often have new bugs. So a patch for a vulnerability very often introduces a new vulnerability that needs a patch. So it's a patch for a patch, and et cetera, et cetera. Keep this in mind. As we are deploying these patches, sometimes it introduces interruptions, and it can actually cause the system to fail. This is why we should test before we deploy. We should have a rollback procedure, and we should also know what patches are needed. If I have 4 applications on this box and only 3 on that box, I need to know that I can't just install 3 on each. I need a 4th patch on this box, things along those lines. Plus it takes time, and it is going to require some bandwidth to download, some resource consumption as you perform the installation, and things along these lines. So we have to allocate sufficient resources to these processes. Next, we're going to talk about bad things that can happen to your computers, your information systems. We're going to look at malware, and we're going to look at various attacks on your systems. First, we have to talk about the virus. The virus is one of the most prevalent pieces of malware. The thing to know about a virus is that it cannot self-replicate. A virus requires a host application to reproduce itself. That definition you should know about a virus. Now, beyond that, there are many types of viruses that trigger on many different things. They attach themselves to an executable. That executable gets carried to some other computer through email or through file downloads, things along these lines. And then once you install that executable on your computer, that virus infects other executables. These executables get copied here and uploaded there and things like this, and that's how a virus spreads. But it attaches itself to these executables. That's how it reproduces. Now, many types of viruses that do many different things too. They have many different types of attacks. Sometimes they're very malicious. Other times it's more of a prank, and it's just to let you know they got one over on you. So they range in their level of maliciousness. They generally are all bad. There's not a good facet to the virus. So you can browse through this list. One that I'll point out is called the polymorphic virus. Polymorphic. Poly, many, morphic, changes. Many changes. This virus changes itself to try and get around the signature database. Once it gets detected, it continually tries to change its signature so that it can violate the antivirus signature engine that recognizes it. And sooner or later, it'll break out into the wild again because it's changed enough that the signature that the antivirus patterns have doesn't recognize this virus anymore. We have a boot sector virus. Now, what made this guy particularly nasty is that very often when a computer system gets really mangled with malware, one of the things that we might do to try and get rid of the malware is we simply blow away the partition and we rebuild the computer from scratch. Well, if the virus has infected the boot sector, that boot sector remains intact. And when we reinstall a new operating system, this virus immediately reinfects the new operating system. We think we cleaned up the box. We've just been reinfected because the virus didn't live in the partition. The virus lived in the boot sector. A couple other types to mention, just a file infector. This is a virus that affects files, system infector, and then script viruses as well. Just different flavors of viruses. Just be aware of these terms. We have transient viruses and resident viruses. A transient virus only is alive while the application is in memory and running. A resident virus will be loaded up into RAM when you launch the application, but even if the application closes, the virus remains in RAM. Now that virus, the resident virus, if we turn the computer off, will go away because it lived in volatile RAM. But he is not bound to the host application that got him launched and loaded up into RAM. So the way viruses work. First, the virus must be distributed. The virus comes to you via file downloads, via an email attachment, something along these lines. A virus on a floppy disk or a CD-ROM or a thumb drive that you plug into your computer. Somehow you get the virus. Now that virus will remain inert until something triggers it. You launch the executable, something along these lines. Now that virus will go reinfect many other things, and it will try to distribute itself to other places through the spreading of attaching itself or infecting files, and then as these files communicate or get copied to other computers, that's how this file gets distributed. And then at some point in time there's a trigger that actually causes the malicious component of the virus to trigger. In one case, it's the Michelangelo virus triggers on Michelangelo's birthday. In another case, it might be when you launch this particular executable, boom, that's when it starts to reformat your hard drive or delete files off the hard drive. So this is the way a virus works. First you get it, then it triggers and it has the opportunity to reinfect other executables, and that's how it finds its way to other computers as well. That's the spreading of the infection. And then finally at some point in time or some event that occurs, boom, that's when that's when the virus actually does its malicious work. The next one we'll look at is called the worm. Now the worm is different from a virus in that it does not require a host executable to replicate. It can reproduce all by itself. That's the most important thing to know about the worm versus the virus. Viruses require a host to reproduce, whereas a worm can reproduce all by itself, does not require a host executable. The way worms are able to infect the computer is through known vulnerabilities. We find one of those vulnerabilities, one of the many that we've talked about today, and the worm will find that vulnerability and then will load itself into the computer system, and from there it can do its malicious work. A logic bomb is a type of malicious software that when some logical event occurs, it could be a certain time and a certain day. It could be we double-click the executable. It could be that we change our wallpaper. Some event, some logical event triggers the execution of the malware. And then the last on this slide is the Trojan horse. Now, a Trojan horse is generally a program that appears to be useful and viable, something we really want. Yet, tucked inside this worthy piece of code is some malicious code. So we think we're running this new game called Whack-A-Mole, and really what we're doing is we are actually notifying a bad guy, hey, I've just infected another computer, come get me when you get a chance. That was actually prevalent back in the old bulletin board days. A program called Whack-A-Mole was readily distributed. It was a game, and I'm sure you probably are familiar with it, but this game that was freely distributed actually had this phone home, come get me, open up a back door so that the bad guy could take over the victim's computer system. So some examples of Trojans you probably wouldn't even recognize. Why? Because they are executables that you think are worthy. You launched these on purpose because you wanted that thing to be running. It's a good program as far as you can tell. The problem is it has malicious code inserted into it. So a bad guy will take an application like Internet Explorer and will inject malicious code into it. Now when you launch your Internet Explorer, you just launched his malicious code. That is a Trojan. Now the more sophisticated attack tools are blended malware. So if a bad guy can find a vulnerability on your computer, he breaks in with just a little bit of authority. And then he's going to try to escalate his authority by launching new services that have a higher level of privilege and things along these lines. He can break into that service and boom, now he's the local administrator, for example, on the box. As soon as he can get sufficient privilege to actually move around on the box a little bit, he will typically, from the victim's computer, download his rootkit, his blended malware. Now, a rootkit is a whole collection of malicious software, Trojaned system files, other executables that launch in the background and remain hidden. They don't report on Task Manager or any of the other surveying tools. So there's a whole collection of these, and a bad guy might open up 5 or 10 or 15 different backdoors, different ways that he can get back into your system, because you might get dumb lucky and fix one, or you might not launch that particular application. So he's gonna spread these backdoors around so that at some point or at any point he'll have 1 or 2 or 5 or 10 different ways to get back into your computer. Further, what a bad guy will do at this point is he will very often harden your computer. If you were dumb enough that you let this guy break in, what's to stop some other bad guy from breaking in? So what he's going to do is he's going to patch your machine, and he's going to reconfigure your box so that other bad guys can't break in and take his computer away from him. That's the bad guy talking about your computer. So again, these are some of the routines that a bad guy will perform when he can break into your machine. Is he will, from your machine, download to your machine. It would be an upload from his perspective, but since he's pulling it from inside, the firewall will allow it. He's going to download his rootkit, that's this blended malware, which is a whole collection of malicious tools. Now, some of the more famous ones are the Back Orifice, NetBus, and Sub7. We're going to take a little bit closer look at these. The Back Orifice tool was very powerful and came out of nowhere, it seemed. In this particular story, A bad guy broke into some kid's computer that was in his bedroom. This computer was set up with a camera, a digital camera. And as a result, the bad guy could take over the camera, and since he could see the desktop, he could actually watch what the camera was seeing. And he literally was monitoring what this kid was doing with his girlfriend in his bedroom. At some point, the kid came over to his desk, and the bad guy actually sent him a message. And he said, "Hey, dude, what are you doing there? I'm your computer. We don't talk too much, but let me ask you this. Please put on your shirt," etc., etc. And meanwhile, the kid is looking like this. That's a true story. This was actually an attack that occurred, and the bad guy recorded this, and that's the look on the guy's face, the victim's face, when he realized his computer actually wasn't his computer any longer. Here's a screen cap from the NetBus utility, and look at all the bad things you can do. Now, you push one of these buttons, you're actually doing this on the victim's computer. So this is the console that the bad guy has on his machine. He's compromised your machine. He can do all these things on your machine. That's what NetBus does for you. That's what most of these tools will do for you. They can view what's on your display. They can log what your keyboard is doing. If you have a microphone, you see the listen button. All sorts of controls and commands can be done remotely through these tools. Now, another type of virus is referred to as the Mimi virus. Now, the Mimi virus is nothing more than a hoax. This is simply somebody starts a rumor that there's a new virus out, and they might name it after their cat or something like that, just to see how much attention they can get their cat's name up on the CNN, perhaps, if this hoax, this new outbreak of a virus spreads, because people watch the blogs, they watch these chat rooms and things like this, and somebody will just announce that, hey, there's a new virus out, everybody, you need to go here and download this file and blah, blah, blah. The next thing you know, 500,000 people across the country are now searching around for this virus, and they're polling each other, hey, where do you find that file? I can't find the fix for it. The next thing you know, they're consuming man hours and resources. Truly, these even cost money. Even though there never really is a virus, they still cost money and productivity. Next, we're going to discuss briefly some ways to detect malware, and then we're going to look at some specific types of attacks that are implemented on your information systems. We have many different types of malware protection, including intrusion detection systems. We can run hashes of our files to validate that our files haven't been modified. And we also run immunizer types of software such as antivirus and anti-spyware software. These are some types of things we can do that detect and then can eradicate some of the malware on our systems. We shouldn't consider that these are complete. They are good, they're better than nothing. They might be 85% or 95% or even 99.9% complete, but there always is a day zero infection that could occur, and that means that there isn't a signature for it yet in the antivirus database, but you have the virus. So again, don't consider that if you have all these pieces in place that you're certain to be protected. It's not a guarantee. One way that these detection devices can identify problems is by signature scanning. Now, signature scanning is only usable on known attacks. We can only have the signature in the signature database if I've seen this attack before, if I've seen it and can recognize it. That's how this particular type of scanning is effective. So signature scanning is not good for new viruses, only viruses that I've seen before. And it very often will transmit or send out a red flag, an error, and it could be a mistake. Sometimes it has a false positive or a false negative type of error. So a false positive is, hey, there's a virus, only it's not really a virus. And a false negative is a virus slips by and it didn't spot it. So these are two different types of errors that these scanning engines can generate. We can also detect malicious activity by monitoring for these activities, such as suddenly the hard drive is full. I had 200 gig free yesterday. Today I only have 50 gig free. What happened? What could have happened is a bad guy might have broken into the system through some vulnerability in the software and now has repartitioned and created a hidden partition where he's actually put together an FTP site, and you're now an FTP server for content you don't know about. This is a bad thing. There are many ways that these consumption of resources, suspicious activities, protocols that shouldn't be on the network, these are the types of things that you can look for and help to identify that something unusual is happening here. And basically this is just a flag for you to start to investigate. We don't exactly know what's going on yet, but we know something might be going on because of this abnormal behavior. We can monitor for changes as well. Suddenly a file that was 100K is 100 meg. And things along these lines. This identifies the possibility that this file has been Trojaned, that there's actually some malicious software tucked inside of it. Configuration modifications. I used to have my firewall turned on. Today it's turned off. Why is that? This could be an indication that a bad guy has broken into this box and is now trying to knock down your defenses so that he can break in with a higher level of privilege and take over the box. Another way we can monitor for changes is by using hashing values or cyclic redundancy check values, CRCs. These will identify a specific fingerprint for a specific file. And if anything modifies that file, then the CRC value for the modified file won't match the original CRC value. Again, these hash values or digests or CRCs, those are all synonymous. If these values change from a known good value to now it's a different thing, that means that new file has been modified and it probably needs to be replaced with an original file. By the way, I would run a more thorough scan than just that. If the guy's replaced one file, he's probably replaced 50 files, and you need to find them all. Next, we're going to look at all sorts of other types of bad stuff that a bad guy is going to do to your systems. We're going to get covert channels, backdoors, timing attacks, race conditions, buffer overflow, and rootkits. We've already talked about some rootkits already. We're going to look at the passive attack. A passive attack says I'm simply listening. I'm not actually touching or probing. All I'm doing is I'm absorbing information. Now, this eavesdropping is substantially easier on a wireless network. If the wireless network is set up and it's not encrypting data, all I have to do is turn on my wireless sniffer and I can record 100% of your information. Another way to eavesdrop is by putting an inductive cuff around an Ethernet cable. And this inductive cuff, without touching any metal or plugging into the wall, you can actually sense the data signals pulsing through the wires, and you can actually pick data out of the wires. These are forms of eavesdropping. Another one is running a network sniffer. Another way to eavesdrop or doing a passive attack is simply to go to the guy's website and do view source and look through the HTML and try to break into this directory browsing function that I described earlier. These are all passive attacks where you're just an anonymous guy and you're just looking at content that he's making available to you. So it's innocent, you're still anonymous, you're not probing, you haven't done anything that should trigger a red flag. Now when we roll into active scanning, this is where we are actually doing something. This is where we risk detection. This is where I'm implementing a denial of service attack, or I'm starting to scan the victim's computers to footprint and then later fingerprint. Much more defined is the fingerprint, where I actually might be trying to modify the data and actually throw an exploit at a perceived vulnerability. This is the active attack, and this is where I detect, or I am subject to detection by an intrusion detection system or just an alert administrator or user. Some other things we need to consider are covert channels. Now, there's this thing called an overt channel. An overt channel is a communications path that was designed to be a communications path. This would be a VPN, for example, or an Ethernet cable. That is the overt communications channel. This was a channel designed for communications. A covert channel is a channel that is being used for communications that it never was intended to be used for communications. There's a certain movie where one guy has to communicate with another guy, only they don't know how to contact one another just in case they get captured. But what they do is there's a certain mailbox that's on a certain corner. And if they put a black mark on this mailbox, the other guy is supposed to check that mailbox every day. And if he sees that black mark on the mailbox, that black mark says, meet me at the coffee shop for a meeting at 4 o'clock. So this would be a covert channel of communications. We have covert storage channels. The example I just gave you was a covert storage channel. I use this mailbox and the fact that I just wrote this big black X on this mailbox, I stored this information on this device that wasn't really intended to communicate to my partner, but I'm using this device to communicate with my partner. That is a covert storage channel. I stored my black X on this mailbox. That mailbox wasn't designed to hold that black X, but I did it anyhow. There is also a covert timing channel. Now, a great example of a covert timing channel, I was just watching a James Bond movie, Thunderball, and the bad guy stole 2 atomic bombs. And he says, if you don't pay me $100 million, I'm going to detonate one of these someplace you don't want me to detonate it, and then I'm going to sell the other one to somebody else, the bad guys. And if you agree to my terms, ring the bell for Big Ben in London, ring him 7 times at 6 o'clock. This is the manipulation or the modulation of a resource, the chiming of the clock. I'm modulating that to communicate with the bad guy. So when the MI6 decides to ring the Big Ben bell 7 times at 6 o'clock, to the rest of the world it was just a freak occurrence. But to the bad guy, this was a direct communication. So this is a covert timing channel. Now the back door we've discussed a few times already. A back door is a way that a bad guy or even a good guy can get into a system bypassing normal access controls. Now, when a good guy uses a back door, it's called a maintenance hook, and typically we're talking about a program developer who built this back door into his program so that he can now go test his code and get it refined until it works right. And then he should pull his back door out, his maintenance hook out. However, very often they don't do that. It takes too much time and it's not part of the project. The project is to make it work and get it out the door fast. Other backdoors are injected into a system on purpose, and they're generally injected into the system through this malicious code inserted into a good piece of code, and that's called a Trojan horse. So I take one of your system files that you need every time, and I will inject into that my malicious code. In other words, I replace your .exe with my .exe. It still does everything you want it to do, but it's also going to do the bad things that I want it to do. And one of those bad things is I open up this vulnerability so that I can get into your computer now. That's a backdoor. And I get into your computer, by the way, bypassing normal access controls. An asynchronous attack. An asynchronous attack generally is considered to be this time of check and time of use. And this would be where I perform a security evaluation and I authorize your access, but before you access it, I modify the data. So let's imagine you want to touch a brownie recipe, and I authorize your access to that brownie recipe. But before you go read the file, I replace it with a top secret document. So you've already been authorized to open the file. I've only substituted a different file. So that's this time of check, time of use. After you've been authorized to open the file, I substitute a different file, and then when you access it, you're actually accessing this top secret document. So this would be a time of check, time of use. This would be an asynchronous attack. Another example up here at the top talks about you're paying a bill at a cash register for $100. You count out the 5 20s, and when the cashier turns around to get you your receipt, you tuck one of the 20s back in your pocket and you hand them the stack of 4 now. You grab your receipt and your product and you leave. So you've just stolen 20 bucks from this guy by the difference between time of check. They saw you hold the 5 bills versus time of use when you actually pay the guy. So that's another classic example of time of check versus time of use, an asynchronous attack. Another type of attack is called the race condition. Now the race condition is where I have 2 processes. Generally one should lead the other. One should happen first and then the other should happen second. But what I do is I attack this first one and slow it down so that this guy might be accomplished first. I will say that for the most part in the race condition, this is more of an academic example. There's kind of a variant of the race condition that was kind of prevalent back in the late 80s, mid to late 80s, on firewalls. Now you realize that a firewall typically has 2 ports, a public side and a private side, and its job is to validate whether or not we want to forward a frame from the outside to the inside and from the inside to the outside. So we use firewall rules to make this decision on whether or not we're going to forward this information through the firewall service. Well, back in the mid to late 80s, there was a whole family, and by the way, from different manufacturers, which is kind of the surprising thing, vulnerability that if I flooded the firewall with a certain type of traffic, the firewall service would fail. And as a result, this box became a router with no rules. What is it? He's just automatically going to, anything inbound, he's going to hand it over here. Anything outbound, he's going to hand it over there. The rule base is now down for about a 5-second period until this firewall service gets its act together and restarts. So what would happen is a bad guy would attack this box and flood it with this particular type of frame that caused the firewall service to crash. And then during the 5 seconds when the firewall was not paying attention because it was knocked down, this is when the bad guy would inject his malicious code through the firewall, and then the firewall service would kick back up and would stop any inbound malicious activities. But meanwhile, the bad guy's already gotten his agents into your private LAN. Now, the buffer overflow attack is a whole other beast. This guy is probably the most prevalent attack of all time. This guy could be 100% eliminated if programmers would validate 100% of user input. We'll talk about this on the next slide. We're going to get into the gory details about how the buffer overflow works. So, the anatomy of a buffer overflow. On this first slide, we're going to look at how a buffer is supposed to work. Now, the buffer is actually this blue block that's in the middle. It's actually called a stack, more accurately. And what happens is, remember how in earlier domain relative to system security architecture, we talked about how an application launches a process, or one or more processes, and each of those processes launch threads. And those processes are assigned or allocated resources. One of the resources that the process is allocated is called a stack. That's where we are right here. So what we have inside that stack on the top half is a process. The blue section there is a single process. That first variable there that's aligned with the bullet, the yellow dot number 2 is, let's imagine that that's our instruction, machine language instruction that's going to go into the CPU, the purple box off on the right. And he's going to get work done. And then he's going to get work done based on the variables that are above him. But that very bottom thing is called a return pointer. Now, what that return pointer does is that says that when you finish doing all the work in this stack, CPU, purple box, when you finish all that work, you let me know, and I'm going to use the return pointer to tell the application what he's supposed to do next. That's what the return pointer does. Now, interesting thing about the stack is when we are loading the stack with the return pointer, the instruction, and then any application supplied variables, those load from the bottom up. But when user input is put into the stack, that would be some other variable that we're waiting for to complete the processing of. That information is input from the top down. And if I don't validate that user input, a bad guy can put in as much data as he cares to, which overwrites all my variables and my instruction and my return pointer. So that's where the problem comes in. If I don't validate user input, what I should do on this program is we have return pointer, instruction, application data, but then I got 2 slots for user data, for example. Let's imagine those are 8 bytes apiece. I should say if you're trying to send me more than 16 bytes of data, truncate everything over 16 bytes and throw it away. Or simply error out and tell the guy, you need to knock this down. I only need 16 bytes of data. Somehow you need to error out and disallow more than 16 bytes. Because what happens is when I don't validate that user input, the bad guy will simply write down over top of all of my stuff and cause the buffer overflow. We'll get to that part of it in a second. So again, the way this should work is application launches a procedure or a process. That process gets allocated a stack. Return pointer is the very first thing, instruction, a variable or 2, then room for user input. That's what the stack is. And that information, once we get it all together, the control unit dumps that stuff into the CPU, it gets processed, output comes back out, and we get notified back to the return pointer, I'm all done. The CPU says, I'm all done. Now the return pointer says, hey, program, application, here's what you're supposed to do next. That's what this slide is showing us. Now, the way a buffer overflow works. is like this. The way a buffer overflow works is because we haven't validated the user input, and I'm letting the bad guy type anything he wants into the telephone number field, for example, because I didn't say just 10 characters and only numeric values. I didn't restrict it in any way. The bad guy simply types in as much garbage as he wants to, but in the middle of that garbage, you see he tucks in a piece of malicious code, a bad instruction that says, contact me, open up a back door for me. And then he inputs more garbage, and then he overwrites the program's return pointer, and he directs that return pointer to point to his own malicious code. So now when the CPU finishes doing its work and it comes back to the return pointer and says, hey, I'm all done, here's your output, the return pointer says, go launch malicious code. Boom. That's how the bad guy performs the buffer overflow attack. And remember, the program stuff from the inside loads from bottom up. User input loads from top down, and that's how it continues to overwrite that instruction and eventually the return pointer. And what the bad guy will put in the middle of this garbage is his malicious code that will return back a command prompt on this server that he just broke into, or it could force this computer to download some malware and launch it, and now he's opened up 5 new backdoors, things along these lines. Whatever the bad guy can tuck into the buffer, that's what this program is going to do as soon as the CPU is done working on whatever that last instruction was. That's the anatomy of a buffer overflow. Another form of attack is called network traffic analysis. Now, this is very often done to perform aggregation and inference attacks. I'm not actually looking at the data that is the traffic. I'm simply looking at the traffic. I don't know where the frames are going necessarily. I don't know what's inside the frames. But what I see is a whole lot of frames, more frames than are normal. This signals to me something. And I take that one detail and I aggregate it with 2 or 3 or 4 other details. And the next thing you know, I can infer information that I'm not authorized to know. So again, network traffic analysis, or even just traffic analysis, is a way to come to a conclusion about information that you're not authorized to know. Classic example is 6 o'clock, the Pentagon parking lot is way full, and there's a whole line of pizza delivery trucks showing up. What does this tell you? That tells you the Pentagon is working overtime tonight. Something must be up. And this could be enough information that I aggregate with 4 other details, and suddenly I know my homeland is under attack or something along these lines. So again, this is a traffic analysis attack, and it leads to aggregation and inference attack. And again, this could be divulging more information than I care for you to know. So the way to defend against traffic analysis, the way to defend against aggregation and inference attack, well, aggregation and inference, we already talked about polyinstantiation. That's a form of padding. I'm telling you a story that is a decoy story. In the case of traffic padding, where suddenly I have this high level of traffic and you notice that, well, maybe I should send out a high level of traffic all the time, and it's just garbage packets for the most part. But now when I have a large amount of real data, I can send them and you can't tell the difference. So it's a way of padding the environment with noise or with decoy information so that the bad guy can't tell when real information is going. Another form of padding has to do with the wireless arena or with emanations protection. What I do is I flood the room with radio frequency white noise, and as a result the emanation signal is this big, but the noise signal is this big, and as a result the bad guy can't tell what the data is because the noise is too loud. That's another form of padding. Now, we had mentioned rootkits before. A rootkit is a whole collection of blended malware, and it's designed to give me 10 or 15 or 20 different avenues back into your computer. And you also remember that we talked earlier about user mode versus kernel mode, how kernel mode is more trusted and has access to more resources. User is least trusted and has access to less amount of resources. I have 2 different types of rootkits. Now, I have a user mode rootkit that runs at the application layer, ring 3 of the ring structure, or the application layer, and it has a smaller security domain, smaller amount of trust, smaller amount of access, but it still is a rootkit, and it still may get me into the box and get me sufficient level of access. However, if I can inject a kernel mode rootkit, this is where I have my malicious software embedded in the kernel of this operating system. This is substantially stronger as a piece of malware. Why? Because the kernel is the most trusted entity, and now the most trusted guy in the box is my buddy. He's my mole, my agent inside your computer, and he's the most trusted guy in the box. So again, it's better if I can, from a bad guy's perspective, it's better if I can inject a kernel mode rootkit versus a user mode rootkit because of the higher level of trust. And here are some examples of well-known Trojaned files. There were numerous attacks where these files were injected with malware and then got distributed to numerous hundreds, perhaps hundreds of thousands of computers. And now when you launched, for example, telnet.exe, what it actually did was it launched telnet, but it also phoned home and told the bad guy, hey, here's a back door for you, come get me. And so these are a whole slew of most of these, from what I gather, yeah, I see a handful of them there. Most of them are on a Unix or Linux computer. Some of them are also used on Microsoft operating systems as well. But again, these were well-known Trojan files that were actually implemented in true attacks.